Hello there and welcome to Life Beyond Seen, where the deepest questions tend to live in the deepest places, and the quietest corners of the world often turn out to be the most extraordinary ones. Imagine standing at the edge of a cliff. Not a dramatic, picturesque cliff above some green valley, but a cliff that drops into absolute darkness, into cold, into a pressure so immense that the human body would be destroyed in an instant. Now imagine that cliff is underwater. Now imagine that it stretches for over 2,000 kilometers in a long curving line beneath the northwestern Pacific Ocean, and that almost nobody is talking about it. That is where we are going tonight. There is a place in the ocean called the Kuril Kamchatka Trench. It sits east of a chain of volcanic islands and a peninsula in Russia's far east, curving through some of the most geologically violent and meteorologically hostile waters on the planet. It reaches depths of approximately 10,500 meters. That is deeper than the height of Mount Everest above sea level. And yet, if you mention this trench to most people, even people who are casually interested in the ocean, you will probably get a blank look. The Mariana Trench is famous. It has been in documentaries, in popular science books, in headlines. James Cameron descended to its deepest point in a submersible in 2012. People know its name. People know that it is the deepest place on Earth, and it is genuinely remarkable. But the Kuril Kamchatka Trench, which is not that much shallower, which is actually longer, which sits in a region of extraordinary geological and biological significance, has remained almost invisible to the wider world. It has not been the subject of a famous solo dive. It has not captured the public imagination in the same way. It sits in a kind of quiet obscurity, which is strange when you consider what it actually is. Tonight we're going to spend some time with this trench, not rushing through it, not ticking off facts, just sitting with it, understanding it slowly, thinking about what it is, what it contains, and why, despite everything we can do with modern technology, it remains so poorly explored. Before we go any further, I want to ask you something simple. Where are you right now? Are you lying in bed with the lights off, listening through headphones? Are you somewhere with a window, and if so, can you see any stars? What time is it where you are? I always find it interesting to think about the different places people are when they listen to something like this. Someone in Tokyo, someone in Toronto, someone in a small town in Germany or Brazil or New Zealand, all listening to the same quiet description of a place none of us have ever seen and almost certainly never will. There is something a little beautiful about that. If you're new here, welcome. Life Beyond Seen is a channel about places, ideas and things that exist just beyond the edge of everyday attention. If this kind of calm, detailed storytelling is something you enjoy, it would mean a lot if you hit the like button and if you subscribe so you can find us again. It genuinely helps the channel, and it takes about 2 seconds. Okay, that is enough of that. Now, back to the trench. The Kuril Kamchatka Trench runs for roughly 2,200 kilometers in a long arc through the northwestern Pacific Ocean. To put that length in perspective, that is approximately the distance from London to Moscow, or from Los Angeles to Kansas City. It is not a small feature. It is one of the largest geological structures in the ocean, and it sits in a part of the world that is, in almost every sense, difficult to reach and difficult to work in. The trench lies east of the Kuril Islands, which are a chain of volcanic islands stretching from the northern tip of Japan's Hokkaido Island up toward the Kamchatka Peninsula in Russia's far east. If you have never looked at a map of this region, it is worth doing. The Kurils form a graceful, slightly irregular arc, like a string of dark beads laid across the water between two larger landmasses. They are dramatic islands, volcanic, rugged, frequently foggy, with very small human populations and a history that is, to put it gently, complicated. But we will get to that. East of these islands, the seafloor drops away, and it does not just drop a little, it plunges. The continental shelf gives way to the trench proper, and the descent is steep and in places almost sheer. The deepest confirmed point in the trench is called the Vityaz Deep. It sits at approximately 10,542 meters below sea level. That measurement was made by Soviet researchers and the name comes from the research vessel that made it. We will talk more about those expeditions later, because they are genuinely important and genuinely underappreciated. 10,500 meters. It is worth pausing on that number for a moment, because it is the kind of figure that is easy to say and hard to actually imagine. The deepest that recreational scuba divers typically go is around 40 meters. Professional saturation divers, working in pressurized suits and chambers, can reach around 600 meters in extreme cases. The deepest any crewed submersible has gone in this trench is a fraction of the total depth. The rest is darkness and pressure and cold, and we have never directly seen most of it. And here is what I think is so interesting about this. We live in an era when people have walked on the moon, when we have sent spacecraft to the edge of the solar system, when we have mapped the surface of Mars in extraordinary detail. We have photographs of the rings of Saturn that are genuinely beautiful. We have detected gravitational waves from colliding black holes 1 billion light years away. And yet, there is a place on our own planet, in our own ocean, that is over 2,000 kilometers long and over 10 kilometers deep, and we have explored only a tiny fraction of it. Not because we are not curious, not because the science is not important, but because it is, in almost every practical sense, extraordinarily difficult to reach. That difficulty is not just about depth. That is the thing. If it was simply a matter of depth, the challenge would be purely technological. Build a stronger submersible, engineer better materials, solve the pressure problem, and you can go deeper, and people are working on that. But the Kuril-Kamchatka Trench is not just deep. It is deep in a place that is geologically violent, politically complicated, meteorologically brutal, and geographically remote from the major oceanographic institutions that have the equipment and funding to attempt serious exploration. Every one of those factors, on its own, would be a significant obstacle. Together, they form something more like a wall. This is a place that does not want to be explored, not in any mystical or intentional sense, obviously. The trench does not have intentions. It simply exists, as it has existed for tens of millions of years, indifferent to whether anyone ever descends into it. But the conditions surrounding it, above it, beneath it, and around it politically and logistically, have combined in a way that has kept it largely beyond human knowledge. And that, I think, is worth thinking about carefully. There is a tendency, in the way we talk about exploration, to assume that the unknown is simply waiting to be discovered. That it is out there, patient and accessible, and that curiosity plus technology plus funding equals answers. And often that is roughly true. But the Kuril-Kamchatka Trench is one of those cases where the gap between wanting to know something and actually being able to find it out is genuinely enormous. Scientists who study this region are not incurious. They are not underfunded by choice. They are not failing to try. They are working against a combination of obstacles that is, by any honest assessment, formidable. So what is the trench exactly? What made it? What lives in it? What does its sediment record contain? What has actually been attempted, and what has been found? What keeps happening every time someone tries to get close to it? And what does it mean, in a broader sense, that a place like this exists in the 21st century, largely unexplored, at the bottom of our own planet? Those are the questions we're going to work through tonight, slowly, without rushing. There is no hurry. The trench is not going anywhere. I want to be clear about something before we go further. This is not a story about conspiracy or cover-up. There is nothing sinister about the fact that this trench is poorly explored. It is not being hidden. It is not being deliberately ignored. It is simply a place that is extraordinarily hard to reach and work in, and the resources required to do so properly have not consistently been available. The story of why is, I think, genuinely fascinating, and it involves geology and geopolitics and engineering and weather and history all at once. But it is a story about difficulty, not secrecy. It is also, in a quieter way, a story about patience. Deep-sea science moves slowly. It has to. The ocean is not a place that rewards impatience. Expeditions take years to plan and fund. Equipment takes years to build and test. A single dive to the deepest part of a trench can take an entire day just for the descent and ascent, leaving only a few hours of actual observation time at the bottom. And if something goes wrong, if a cable fails, if a storm rolls in, if equipment is lost or damaged, the setback can be enormous. There are ROVs, remotely operated vehicles, that have been lost in these depths. There are instruments that have imploded under pressure that their engineers thought they could handle. This is not easy work. It is some of the hardest scientific fieldwork that exists, and yet people keep trying. Because what is down there, in the darkness at the bottom of the Kuril-Kamchatka Trench, matters. It matters for our understanding of geology, of plate tectonics, of earthquake history, of how life adapts to extreme conditions. It matters for understanding the deep ocean as a system, which in turn matters for understanding the planet as a system. The trench is not just a hole in the seafloor. It is an archive, it is a habitat, it is a record of everything the Earth has done in this part of the Pacific for tens of millions of years. We just cannot read it very well yet. There is something almost poignant about that, I think. Not in a sad way, exactly. More in the way that any honest acknowledgement of human limitation has a certain quiet weight to it. We are curious creatures. We have built remarkable tools. We have gone to extraordinary places. And there is still a 2,000-kilometre-long abyss at the bottom of the ocean that we have barely touched. Let us start at the beginning then, with the trench itself, with the rock and the water and the forces that made it, and that continue to shape it every single day. Because before we can understand why exploration is so difficult, we need to understand what we are actually dealing with. And what we are dealing with is something that was not built gently. The Kuril-Kamchatka Trench is a product of one of the most powerful forces in geology. Two enormous plates of the Earth's crust, moving against each other over millions of years, one sliding beneath the other in a process that generates earthquakes and volcanoes and eventually trenches exactly like this one, the Pacific Plate moving westward, meeting the Okhotsk Plate and diving beneath it. The seafloor bending downward under its own weight, pulled into the mantle, creating a long, deep scar in the ocean floor. That process is still happening. Right now, as you listen to this, the Pacific Plate is moving, slowly by human standards, a few centimetres a year, but relentlessly. And the trench is the visible result of that movement, the place where the ocean floor folds downward and disappears into the Earth's interior. It is, in a very literal sense, a wound in the planet, and like many wounds, it is not quiet. The geological character of this trench, the violence built into its very structure, is one of the central reasons why exploring it is so much harder than simply building a vehicle that can withstand the pressure. The trench is not a still place. It shakes, it generates currents, it disturbs sediment, it sits at the intersection of forces that have been shaping this part of the Pacific for longer than most life on land has existed. And that is where we will go next. The Pacific Plate is one of the largest pieces of the Earth's crust. It covers roughly 103 million square kilometres of the ocean floor, and it is moving. That movement is slow enough that you would never feel it standing on a beach, but over geological time it is relentless, and the consequences of it are enormous. The plate is heading generally westward and northwestward, and where it meets the Okhotsk Plate, along the edge of the northwestern Pacific, something dramatic happens. The Pacific Plate, being older and denser, bends downward. It slides beneath the Okhotsk Plate in a process geologists call subduction. The angle of that descent, the rate of movement, the thickness of the crust involved, all of these things determine the character of what gets left behind at the surface. And what gets left behind here is the Kuril-Kamchatka Trench. The trench runs for approximately 2,200 kilometres in a long curving arc from the southeastern coast of Kamchatka in the north down toward the northeastern end of the Japanese island chain in the south. It is oriented roughly northeast to southwest, following the line where the two plates meet. The shape of it, if you could see it from above with the water removed, is not a simple straight groove. It curves, it widens and narrows. It has an asymmetry to it that reflects the complexity of the subduction process that created it. The western wall of the trench, the side closest to the Kuril Islands, tends to be steeper and more dramatic. The eastern wall on the Pacific Plate side is generally more gradual. This asymmetry is common in subduction zone trenches, and it has practical consequences for exploration because the terrain at the bottom is not uniform. It is complicated. The deepest confirmed point in the trench is called the Vityaz Deep, named after the Soviet research vessel that measured it. That measurement, taken in 1953, put the depth at approximately 10,542 metres. That number has been refined slightly over the years as measurement technology has improved, but it remains in roughly that range. To put it in terms that are a little easier to picture, if you placed Mount Everest at the bottom of the Vityaz Deep, the summit would still be more than a kilometre underwater. The depth is genuinely difficult to hold in your mind. It is not just deep in the way that a very deep lake is deep. It is deep in a way that begins to feel almost abstract, a number that requires effort to translate into something physical and real. The formation of the trench did not happen quickly, at least not by human standards. Geologists estimate that subduction along this margin began somewhere between 65 and 80 million years ago, around the time of the mass extinction that ended the age of the dinosaurs. The Pacific Plate has been sliding beneath the Okhotsk Plate for all of that time, continuously, generating the trench and the geological structures associated with it. One of the most visible of those structures is the Kuril Island arc itself. The islands are not random. They are the surface expression of the same subduction process that created the trench. As the Pacific Plate descends into the mantle, it carries water with it, locked into the minerals of the oceanic crust. That water lowers the melting point of the surrounding mantle rock, generating magma. The magma rises through the overlying Okhotsk Plate and erupts at the surface, building volcanoes. Over millions of years, those volcanoes accumulate into islands. The Kuril Islands are a chain of roughly 56 islands, stretching about 1,300 kilometers from Kamchatka to Hokkaido, and almost all of them are volcanic in origin. They are, in a very direct sense, the product of the same forces that carved the trench. The trench and the island arc are two sides of the same geological process. The floor of the trench is not a flat plain. This is worth emphasizing because it is easy to imagine a deep-sea trench as simply a long, featureless groove, like a channel dug into the seafloor. The reality is considerably more complex. The bottom of the Kuril-Kamchatka Trench has ridges and depressions, fault structures running at various angles, and thick accumulations of sediment in some areas, while other areas are relatively bare rock. The sediment comes from multiple sources. Some of it is terrigenous material, fine particles of rock and soil that have been carried from the land by rivers and wind and eventually settled to the ocean floor. Some of it is biological, the remains of tiny marine organisms that lived in the surface waters above and slowly sank after dying, a process oceanographers sometimes call marine snow. Some of it is volcanic, ash layers from eruptions on the Kuril Islands and Kamchatka that have been deposited over thousands of years. These different sediment types accumulate in layers, building up over time into a record that contains, if you know how to read it, an enormous amount of information about the history of the region. The trench also has what are called turbidite deposits. These are layers of sediment that were not deposited slowly and gradually, but were instead transported rapidly by underwater avalanches, triggered by earthquakes. When a large earthquake shakes the walls of the trench, sediment that has accumulated on the slopes can suddenly be set in motion, flowing down into the deeper parts of the trench in dense, fast-moving currents. These turbidity currents deposit distinctive layers in the sediment record, layers that look different from the surrounding material and that geologists can identify and date. They are in effect a written record of past earthquakes, preserved in the sediment at the bottom of the trench. We will come back to that idea later because it is one of the most scientifically valuable things about this trench and also one of the hardest things to access. What is important to understand right now is that the geology of the Kuril-Kamchatka Trench is not static. The subduction process that created the trench is still ongoing, the Pacific Plate is still moving, the Okhotsk Plate is still being pushed and deformed. The stress that builds up along the boundary between them is still being released, periodically and dramatically in the form of earthquakes. The trench is not a geological relic from the distant past that happens to still be there. It is an active structure, in the sense that the forces that shaped it are still operating. The trench is still being deepened and modified, still accumulating sediment, still experiencing the tectonic stress that defines it. It is, in a meaningful way, a living geological feature, and that aliveness, that ongoing activity, is part of what makes it so difficult to work in. There is a detail about the trench's shape that I find worth pausing on. The trench is long and narrow, much longer than it is wide. In cross-section, it is roughly V-shaped, though the V is not perfectly symmetrical. The width at the bottom, in the deepest parts, is relatively modest, perhaps a few kilometres across in the narrowest sections. This means that the walls of the trench are not far away when you're at the bottom. You are, in a sense, inside something, surrounded by walls of rock and sediment rising steeply on either side. This geometry has implications for how sound travels in the trench, which matters for acoustic communication with deep-sea instruments. It has implications for how currents move along the trench floor. And it has implications for what happens when sediment is disturbed, either by an earthquake or by the passage of a deep-sea vehicle. The trench is an enclosed environment in ways that open ocean is not. The Okhotsk Plate itself is worth a brief mention, because it is not the most commonly discussed tectonic plate, and its character has some bearing on the story. The Okhotsk Plate is a relatively small plate, bounded by the Pacific Plate to the east, the North American Plate to the northeast, and the Eurasian Plate to the west. There has been some scientific debate over the years about whether it should be classified as a distinct plate or as part of the North American Plate, and the question is not entirely settled. What is clear is that the boundary between the Pacific Plate and whatever you call the plate it is subducting beneath in this region is one of the most seismically active boundaries on Earth. The convergence rate between the plates is roughly 7 to 8 centimeters per year, which is relatively fast for a subduction zone. That rate of convergence means that stress accumulates quickly and is released frequently. It is one of the reasons why this region has such a dense history of large earthquakes. The Vityaz Deep sits in the southern part of the trench, roughly at the latitude of the central Kuril Islands. It is worth noting that the deepest point of a trench is not always at the centre of its length, and the Kuril-Kamchatka Trench is a good example of that. The trench varies in depth along its length, with shallower sections in the north near Kamchatka and deeper sections in the south. The reasons for this variation are connected to the age and density of the subducting Pacific Plate at different points along the margin, as well as variations in the structure of the overlying plate. Older oceanic crust is generally denser and tends to subduct at steeper angles, which can produce deeper trenches. The Pacific Plate in the southern part of the Kuril-Kamchatka margin is older than in the north, which partly explains why the Vityaz Deep is where it is. All of this geological detail might seem like background information, the kind of thing you cover before getting to the interesting parts. But I want to suggest that it is actually central to the story of why this trench is so difficult to explore. The trench is not just a deep hole. It is a deep hole that was created by, and continues to be shaped by, one of the most powerful and active tectonic boundaries on the planet. Its depth is not incidental. Its location is not incidental. Its ongoing seismic activity is not incidental. These things are all connected, and they all contribute directly to the difficulty of working there. The same forces that made the trench deep also made it dangerous. The same geological activity that gives the trench its scientific value also makes it hard to study. There is a kind of irony in that, though perhaps irony is not quite the right word. It is more like a design feature of the planet that was not optimized for human convenience. The Kuril Island arc, sitting just to the west of the trench, is a reminder of this at every scale. The islands are beautiful in a stark, volcanic way. Many of them are dominated by volcanic cones, some still active, some dormant but not extinct. The same magmatic processes that built those islands are rooted in the subduction happening beneath the trench. The trench and the islands are expressions of the same event, seen from different angles. When a large earthquake ruptures along the plate boundary beneath the trench, the islands feel it. When a volcano on one of the Kuril Islands erupts, the ash eventually settles into the trench. The geological system here is tightly connected across scales, from the microscopic mineral changes happening in the subducting crust to the island-building eruptions visible from space. There is one more physical characteristic of the trench worth noting before we move on, and that is the matter of pressure. Not the abstract concept of it, but the specific mechanical reality of what 10,500 meters of water above you actually means in terms of force. At that depth, the pressure is approximately 1,050 times the atmospheric pressure at sea level, or roughly 15,000 pounds per square inch. That number is almost impossible to intuit directly. The closest analogy I can offer is that it is roughly the equivalent of having 50 jumbo jets stacked on top of every square inch of surface area. Every component of any instrument sent to that depth must be engineered to survive that force without deforming, cracking, or imploding. The trench's depth is not just a measurement of how far down it goes. It is a measurement of how much force must be overcome to work there. And that force is, in large part, a direct consequence of the geology we have just been describing. The trench is deep because the subduction process made it deep. The pressure at the bottom is what it is because the trench is what it is. Understanding the trench as a geological object, as a product of specific forces operating over specific timescales, makes the exploration challenge more legible. It is not just that the trench is far away, or that it is dark, or that it is cold. All of those things are true, and we will get to them. But the fundamental character of the place, the reason it is the way it is, comes from the plate tectonics. From the Pacific plate sliding beneath the Okhotsk plate. From 65 to 80 million years of that process, continuous and ongoing, building a structure that is in some ways one of the most extreme environments on the surface of this planet. And it is not a quiet environment. That is the part that tends to get left out of the picture when people think about the deep sea. There is a tendency to imagine the deep ocean as still and dark and silent, a place of profound calm. In some trenches, in some moments, that image might be roughly accurate. But the Kuril Kamchatka Trench sits in a region where the Earth is, by any reasonable measure, restless. The seismic history of this area is not a background detail. It is one of the defining facts about the place. The trench exists within one of the most seismically active zones on the entire planet, and the consequences of that activity reach all the way down to the bottom of the water column and into the sediment below. That history, and what it means for anyone trying to work in this region, is where we need to go next. The Pacific Ring of Fire is one of those phrases that gets used often enough that it can start to feel like a label rather than a description. A convenient shorthand for a loosely defined zone of geological activity. But when you look at the specific numbers attached to the Kuril-Kamchatka region, the phrase stops being a label and starts to feel like a fairly literal description of something that is genuinely, persistently, and sometimes catastrophically violent. The Ring of Fire traces a rough horseshoe shape around the edges of the Pacific Ocean, following the boundaries where the Pacific Plate and several neighbouring plates are in contact. Along this boundary, roughly 90% of the world's earthquakes occur. About 75% of the world's active volcanoes are found here. The Kuril-Kamchatka region sits along the northwestern arc of this horseshoe, and it is not a quiet section of it. It is, by most measures, one of the most seismically active stretches of coastline and ocean floor on the planet. The subduction happening beneath the trench does not proceed smoothly. Plates do not slide past each other like well-oiled machine parts. They lock together along rough, irregular surfaces, accumulate stress over years and decades, and then release that stress in sudden, violent ruptures. The bigger the locked area, and the longer it has been building, the larger the earthquake when it finally lets go. The 1952 Severokurilsk earthquake gives you a concrete sense of what this means in practice. On the 4th of November 1952, a magnitude 8.3 earthquake ruptured along the Kuril subduction zone. The epicenter was located in the ocean east of the Kamchatka Peninsula, not far from the trench. The earthquake itself was enormous, one of the largest recorded in the 20th century at that point, but the immediate shaking was only part of the story. Within minutes, a tsunami had been generated. The waves reached the city of Severokurilsk, located on Paramshir Island in the northern Kurils, and essentially destroyed it. Estimates of the death toll vary, partly because Soviet authorities at the time suppressed information about the disaster, but the number of people killed is generally placed in the range of several thousand. The city was rebuilt, but on higher ground, and the event left a mark on how the region understood its own vulnerability. What's worth pausing on here is not just the human tragedy of that event, though that matters. It is the scale of the energy involved. A magnitude 8.3 earthquake releases roughly 30 times more energy than a magnitude 7.3 earthquake due to the logarithmic nature of the scale. The rupture zone for an event like that can extend hundreds of kilometers along the plate boundary. The seafloor can move vertically by several meters in a matter of seconds. For any equipment sitting on or near the trench floor, that kind of event is not an abstract hazard. It is a physical force that can shift sediment, generate internal waves, alter currents, and in the worst case simply bury or destroy whatever was placed there. The 1952 earthquake was not an isolated event. In 2006, a magnitude 8.3 earthquake struck the central Kuril Islands region. Less than 2 months later, in January 2007, another earthquake of magnitude 8.1 hit roughly the same area. 2 major earthquakes in the same subduction zone within weeks of each other is unusual, even by the standards of the Ring of Fire, and both events generated tsunamis. The 2006 tsunami caused damage as far away as Hawaii and the California coast, though the effects were relatively minor at those distances. Along the Kuril Islands themselves, the waves were more significant. The pair of events in 2006 and 2007 demonstrated something that seismologists had been discussing for years. The Kuril subduction zone does not release its stress evenly or predictably. Different segments of the plate boundary have different locking behaviours, different recurrence intervals for large earthquakes, and different potential for generating tsunamis. Understanding which segments are most dangerous and when they are likely to rupture requires the kind of long-term seafloor monitoring that is extraordinarily difficult to maintain in this region. Kamchatka adds another layer to all of this. The peninsula is one of the most volcanically active land masses on Earth. There are over 300 volcanoes on Kamchatka, and approximately 29 of them are considered active in the sense that they have erupted in recent historical time or show ongoing signs of activity. Klyushevskaya Sopka, at roughly 4,750 meters, is the highest active volcano in Eurasia and one of the most continuously active volcanoes anywhere on the planet. It erupts frequently, sometimes multiple times per year. Shivalok, another Kamchatka volcano, has been in a state of near-continuous eruptive activity for decades, producing ash clouds that can reach into the stratosphere and disrupt aviation across the North Pacific. Bezimiany, which had a catastrophic eruption in 1956 that was structurally similar to the 1980 eruption of Mount St. Helens, remains active today. The Kuril Islands themselves carry a chain of volcanoes running the full length of the arc, most of them products of the same subduction process that created the trench. Some of the islands are essentially just the tops of large submarine volcanoes, their bases sitting on the ocean floor far below sea level. The volcanic activity along the arc is directly connected to the subduction happening beneath the trench. As the Pacific plate descends into the mantle, it carries water locked into its minerals, At depth, that water is released into the overlying mantle wedge, lowering the melting point of the rock and generating magma. That magma rises through the crust and eventually erupts at the surface, building the volcanic arc. The trench and the volcanic chain are not separate phenomena. They are two visible expressions of the same hidden process. For anyone trying to conduct scientific work in this region, the volcanism matters in a few specific ways. Volcanic ash falls into the ocean and settles to the sea floor, creating distinct layers in the sediment record. These ash layers are actually scientifically valuable. They can be dated and used as time markers when interpreting sediment cores. But active eruptions also create hazards for research vessels operating in the area. Ash clouds can reduce visibility and interfere with navigation. Volcanic gases can affect air quality on deck. Underwater volcanic activity, including hydrothermal venting and submarine eruptions, can alter local water chemistry and temperature in ways that affect instrument readings. The volcanic environment is not simply a backdrop. It is an active variable in the research environment. Then there is the continuous low-level seismic activity, the microseismic background that never really stops in a subduction zone. Between the large earthquakes, the plate boundary is not still. There are constant smaller ruptures, magnitude 3s and 4s and 5s, too small to cause significant damage at the surface but persistent enough to be measurable. This microseismic activity has direct consequences for equipment operating on or near the trench floor. Pressure waves moving through the water column can interfere with acoustic communication systems, which are already operating at the limits of their range and reliability at these depths. Sediment near the trench walls, which in some areas has been accumulating for thousands of years in unstable configurations, can be disturbed by even moderate seismic events. Turbidity currents, dense flows of sediment-laden water that cascade down the trench walls, can be triggered by earthquakes and travel at considerable speed along the trench floor. A turbidity current of any significant size would be immediately destructive to any instrument or lander sitting on the bottom. The 2011 Tohoku earthquake, which struck the Japan Trench to the south, provides a useful illustration of how seismic events interact with trench sediments. After that earthquake, researchers examining sediment cores from the Japan Trench found a distinct layer of disturbed material, a turbidite, deposited by the mass movement of sediment triggered by the rupture. The layer was clearly visible in the cores and could be dated to the earthquake. Similar turbidite layers from past earthquakes are preserved in the sediment record throughout the Kuril Kamchatka Trench system. This is scientifically valuable, as we will discuss later. But it also means that the trench floor is not a static environment. It is a place where significant sediment movement events happen on timescales that are short relative to the history of the trench, and those events can happen without warning. There is something worth sitting with for a moment in all of this. The popular image of the deep ocean, as I mentioned before, tends towards stillness, darkness and cold and silence. And in some ways, the deep ocean is those things. But the Kuril-Kamchatka Trench sits at the base of a geological system that is among the most energetic on the planet. The surface world above the trench, the volcanic islands, the earthquake-prone coastlines, the storm-battered ocean, is violent in ways that are obvious and well documented. What is less obvious is that the violence does not stop at the surface. It propagates downward. Earthquakes send pressure waves through the entire water column. Turbidity currents carry sediment from shallow water to the deepest parts of the trench. Volcanic ash from eruptions hundreds of kilometers away eventually reaches the bottom. The trench is connected to the surface world in ways that matter for anyone trying to work there. This connectivity also makes the trench scientifically interesting in a specific way. Because the Kuril-Kamchatka region is so seismically and volcanically active, the sediment record in the trench is unusually rich in event layers. Earthquakes leave turbidite deposits, volcanic eruptions leave ash layers. changes in surface productivity leave organic carbon signals. The trench floor is, in a sense, a recording device for the geological and climatic history of the region. But accessing that recording device requires getting equipment to the bottom reliably, recovering it intact, and interpreting the data in a context where the environment itself is constantly adding noise to the signal. The seismic activity that makes the sediment record so valuable is also the activity that makes collecting it so difficult. The relationship between the seismic environment and the exploration challenge is not a simple one-way street either. It is not just that earthquakes make things dangerous, it is that the unpredictability of the seismic environment makes planning extremely difficult. A research expedition to the Kuril Kamchatka Trench might be planned months or years in advance, with a specific weather window identified and a specific set of scientific objectives defined. But if a significant earthquake occurs in the region shortly before or during the expedition, the situation changes rapidly. Sediment plumes can reduce the transparency of the water column, affecting optical sensors. Acoustic conditions can be disrupted. In the worst case, a large earthquake could generate a tsunami that poses a direct threat to the research vessel. These are not hypothetical risks. They are documented features of working in one of the most seismically active ocean regions on Earth. It is also worth noting that the seismic hazard in this region is not uniformly distributed along the trench. Different segments of the Kuril subduction zone have different seismic histories and different levels of current stress accumulation. The 2006 and 2007 earthquakes, for example, occurred in a segment that seismologists had identified as a seismic gap, a section of the plate boundary that had not experienced a large earthquake in an unusually long time and was therefore considered overdue. The rupture of that gap, while destructive, was in some ways a scientifically expected event. Other segments of the Kuril-Kamchatka subduction zone remain in various states of stress accumulation, and the timing of future large earthquakes is, as always with earthquake science, impossible to predict precisely. For expedition planners, this uncertainty is a constant background consideration. There is no moment when the region can be declared seismically quiet or safe in any absolute sense. Kamchatka's volcanoes add a specific aviation hazard that affects how research expeditions are staged. The nearest major airport for accessing the region is in Petropavlovsk-Kamchatsky, and flights in and out of that city pass through airspace that can be affected by volcanic ash clouds from Klushevskaya, Shivolok, or any of the other active volcanoes in the region. Ash clouds are invisible on standard radar and can cause serious engine damage to aircraft. When a major eruption occurs, flight paths are rerouted and airports can be temporarily closed. For a research expedition that depends on flying scientists and equipment in and out of Kamchatka, volcanic activity is not a background detail. It is a logistical variable that can disrupt the entire operation. None of this is meant to suggest that the region is impossible to work in. People live in Kamchatka. Fishing fleets operate in the waters above the trench. Russian military installations exist on several of the Kuril Islands. Human activity in this region is real and ongoing. But sustained, technically demanding scientific work at the bottom of a 10-kilometre deep trench is a different kind of activity, with different tolerances for risk and different requirements for stable operating conditions. The seismic and volcanic environment raises the baseline difficulty of that work considerably, and it does so in ways that are not always easy to plan around or mitigate. The geological violence of the Kuril-Kamchatka region is, in the end, inseparable from the trench itself. The trench exists because of that violence. It is maintained by that violence. Its scientific value is partly a product of that violence, and its inaccessibility is, in no small part, a consequence of it. To understand why this trench remains so poorly explored, you have to understand what it actually feels like, from an operational standpoint, to try to work in a place where the ground beneath you is one of the most seismically active surfaces on the planet. And that is before you have even considered what the conditions are like inside the trench itself, at the bottom of 10,000 metres of water, in the dark and the cold and the crushing pressure. That is a separate story, and in some ways an even more difficult one. So let us go down there, at least in the way that language allows. Let us try to describe what the inside of the trench actually is, not in geological terms this time, but in physical ones. What the environment feels like, what it does to objects placed inside it, and why those conditions make the work of exploration so specifically and stubbornly difficult. Start with pressure, because pressure is the first thing that defines the Hadal zone. At sea level, the atmosphere pushes down on everything with a force of roughly 1 kilogram per square centimetre. That is what we call one atmosphere of pressure, and it is what human bodies, and most machines, are built to exist within. As you descend into the ocean, pressure increases by approximately 1 atmosphere for every 10 metres of depth. This is a linear relationship, steady and unrelenting. By the time you reach 100 metres, you are at 11 atmospheres. At 1,000 metres, 101 atmospheres. At the bottom of the Kuril Kamchatka Trench, somewhere around 10,500 metres down, the pressure is in the range of 1,050 atmospheres. In practical terms, that is approximately 15,000 pounds per square inch, pushing inward on every surface from every direction simultaneously. To try to make that number feel real for a moment, a standard car tyre is inflated to around 30 to 35 psi. The pressure at the bottom of this trench is roughly 450 times that, pressing inward rather than outward, with no interior volume to provide resistance. Any object that contains a sealed airspace and is not specifically engineered to withstand that load will simply be crushed. Not gradually, not slowly. At the moment it descends beyond the pressure threshold its structure can tolerate, it collapses. Styrofoam cups, famously, are sometimes sent down on deep-sea equipment as a demonstration of this effect. They come back compressed to a fraction of their original size, perfectly preserved in shape, but reduced to something the size of a thimble. It is a useful visual, but the engineering problem it illustrates is not trivial. Building equipment to survive at full ocean depth requires using materials and geometries that can transmit pressure loads without catastrophic failure. Titanium is the standard choice for deep-sea housings because it combines high strength with relatively low density and excellent corrosion resistance in seawater. But even titanium has limits. A titanium sphere machined to hold electronics at depth must have walls thick enough and a geometry precise enough that the compressive load is distributed evenly across the entire surface. Any flaw in the material, any slight asymmetry in the shape, any microscopic crack or inclusion becomes a potential failure point under 15,000 pounds per square inch. The engineering tolerances involved are extremely tight, and the consequences of getting them wrong are total. There is no partial failure at this depth. When a housing fails, it implodes, and whatever was inside is gone. This is not a theoretical concern. In 2014, the Nereus, a hybrid remotely operated vehicle developed by the Woods Hole Oceanographic Institution, was operating at approximately 9,990 metres in the Kamchatka Trench near New Zealand when it imploded. The vehicle had successfully reached full ocean depth in the Challenger Deep in 2009 and had conducted multiple successful dives. Then, on a routine dive in a different trench, it was simply gone. The surface team watched the acoustic signal disappear, and when they recovered the debris that floated to the surface, it was clear what had happened. A pressure failure. The Nereus was one of perhaps 3 or 4 vehicles in the world capable of operating at that depth. Its loss was not just a financial setback, it was a genuine reduction in humanity's total capacity to explore the deepest parts of the ocean. The Kuril Kamchatka Trench reaches depths comparable to the Kermadec. Any vehicle operating there would be subject to the same pressure environment that destroyed the Nereus. That is not a reason to never attempt it, but it is a reason to understand that every dive at this depth is a significant technical and financial risk, and that the pool of equipment capable of taking that risk is extremely small. Pressure is the most dramatic physical characteristic of the deep trench environment, but it is not the only one. Temperature is its own challenge, though in a quieter way. Near the bottom of the Kuril Kamchatka Trench, water temperature hovers somewhere between 1 and 2 degrees Celsius. That is just above freezing. For electronics, sustained cold is not necessarily fatal, but it does affect performance. Batteries discharge more slowly in cold temperatures, which sounds like an advantage until you realise it also means they deliver less power on demand. Lubricants thicken. Seals behave differently than they do at room temperature. Instruments calibrated at surface conditions may read slightly differently in the cold. None of these effects are individually catastrophic, but together they add a layer of environmental stress that engineers have to account for across every component of a deep-sea system. The cold also affects the water itself in ways that matter for equipment design. Cold water is denser than warm water, and at depth, the combination of a low temperature and high pressure produces water that behaves slightly differently from surface seawater in terms of its acoustic and optical properties. Acoustic communication, the primary way that surface ships talk to deep-sea equipment, relies on sound travelling through the water column in predictable ways. But the water column between the surface and the trench floor is not uniform. It has layers of different temperature and salinity that refract sound, bending acoustic signals away from their intended paths. Getting a reliable acoustic link to a vehicle or lander at 10,000 metres in the Kuril Kamchatka Trench through a water column that includes the thermocline, the deep scattering layer, and whatever local disturbances the seismic environment has introduced is genuinely difficult. Commands can be delayed, responses can be lost. The bandwidth available for acoustic communication at these depths is extremely low. We're talking about data transfer rates that would feel familiar to someone who remembers early dial-up internet, except less reliable. Light is gone long before you reach the bottom. The photic zone, where sunlight penetrates in useful amounts, extends to roughly 200 metres in clear open ocean water. Below that, it gets dark quickly. By 1,000 metres, it is essentially complete darkness in the sense that no surface light reaches there at all. The only light in the deep trench comes from bioluminescence, the cold chemical glow produced by organisms themselves, and from whatever lights a research vehicle carries with it. For ROVs and landers, artificial lighting is essential for any visual observation or camera work, but lights consume power, and power at depth is a finite resource. Landers, which typically freefall to the bottom and sit there passively before releasing ballast and floating back to the surface, carry batteries that must last the entire deployment period. The longer a lander sits on the bottom, the more data it collects, but the more power it uses. Balancing deployment time against power budget is one of the routine engineering trade-offs in designing deep-sea instruments. The darkness itself also has a psychological dimension worth mentioning, even in a purely operational context. The trench floor at 10,000 metres is one of the most isolated environments accessible to human instruments. The nearest surface is 2 hours away for a free-falling object. There is no way to physically intervene if something goes wrong. If an ROV gets its tether snagged on a rocky outcrop, the surface team has to solve that problem remotely, using acoustic commands with multi-second delays through a communication link that may not be fully reliable in complete darkness, at a depth where the pressure would destroy any human-rated vehicle that currently exists. The operational environment is one where problems compound in ways that are genuinely hard to manage. The currents near the trench floor add another variable. The Hadal zone is not still. Water moves through the trench, driven by density differences, by the topography of the trench walls, and occasionally by the pressure waves of seismic events. These Hadal currents are not well characterized in the Kuril Kamchatka Trench, partly because so few instruments have spent enough time there to measure them properly. What is known from other deep trenches is that currents near the floor can be surprisingly swift in localized areas, particularly near the trench walls where topographic effects concentrate flow. For a lander sitting on the bottom, a current is mostly an inconvenience. For a tethered ROV trying to hold position and conduct precise sampling, an unexpected current is a serious operational problem. The sediment at the bottom of the trench presents its own set of complications. The floor of the Kuril Kamchatka Trench is not bare rock. It is covered in sediment, fine particles that have settled over millions of years, layered with the turbidite deposits from earthquakes and the ash layers from volcanic eruptions. This sediment is extremely fine-grained and in places very loosely consolidated. When an ROV or lander touches down on the trench floor, it can disturb the sediment in ways that take hours to settle. The resulting cloud of fine particles reduces visibility to near zero for optical instruments and can clog sampling mechanisms. Operating carefully near a deeply unconsolidated sediment surface at 10,000 meters, in the dark, with limited acoustic communication and a tethered vehicle that costs tens of millions of dollars, requires a level of precision that is genuinely difficult to achieve. There is also the simple matter of the trench's physical dimensions. The Kuril Kamchatka Trench runs for approximately 2,200 kilometers. Even if a research expedition managed a successful dive to the deepest point, the Vityaz Deep at around 10,542 meters, that single dive would cover a footprint of perhaps a few hundred square meters of the trench floor. Set against a trench that is roughly 2,000 kilometers long and tens of kilometers wide at depth, a single successful dive is a vanishingly small sample. The biological communities, the sediment structures, the topographic features of the trench floor vary enormously along its length. A sample from one location tells you about that location. It tells you very little about what is happening 200 kilometers away or 500 kilometers away in a different segment of the trench with a different seismic history and a different surface productivity regime above it. This is the spatial problem that haunts all deep trench science, and it is particularly acute in the Kuril Kamchatka Trench because of its length. The Challenger Deep in the Mariana Trench, which has received far more attention and far more dives, is a relatively compact target. The Kuril Kamchatka Trench is not compact. It is a long, narrow, geologically varied system that would require dozens of successful full-depth dives spread across its entire length to begin characterizing with any real comprehensiveness. The number of successful full-depth dives that have actually occurred in this trench can be counted on one hand, with fingers to spare. And then there is the remoteness. The trench is not located conveniently near a major oceanographic port. The nearest significant port is Petropavlovsk-Kamchatsky, on the eastern coast of Kamchatka, and it is a substantial transit from there to the southern end of the trench system. A research vessel leaving port and heading for the trench is already committing to days of open ocean transit through some of the roughest waters in the Pacific before it even arrives at the deployment site. Every day of transit is a day of fuel consumption, a day of weather exposure, and a day of time that could otherwise be spent collecting data. The transit cost, in time and money and fuel, is not trivial, and it compounds all the other challenges. When you add up the pressure, the cold, the darkness, the acoustic communication limits, the sediment disturbance, the Hadal currents, the spatial scale of the trench, and the remoteness of the location, you get a picture of an environment that is not simply deep. It is specifically, comprehensively hostile to the kind of sustained, systematic scientific work that would be needed to actually understand it. Each individual challenge might be manageable in isolation. Together, they create a situation where even purpose-built state-of-the-art equipment is operating near the edge of its design envelope, in a place where recovery from failure is essentially impossible, and the cost of each attempt is measured in millions of dollars and years of planning. It is worth pausing on that for a moment, because it is easy to read a list of technical challenges and come away thinking that the problem is simply one of engineering, that if we build better robots and stronger housings, the trench will eventually yield to exploration in the way that other difficult environments have. And that is partly true. Technology does improve. The equipment available today is significantly more capable than what existed 20 years ago, and what exists 20 years from now will likely be more capable still. But the Kuril-Kamchatka Trench is not waiting for better technology in the way that, say, a distant planet waits for a better spacecraft. It is an active, changing environment whose conditions are set by geological forces operating on timescales that dwarf any human engineering program. The pressure will not decrease. The seismic activity will not quiet down. The remoteness will not shrink. The spatial scale will not contract. Technology can improve our ability to work within those conditions, but it cannot change the conditions themselves. What the physical environment of the trench ultimately demands is not just better equipment, it demands patience and resources and a sustained institutional commitment to working in a place where progress is slow and setbacks are expensive. That kind of commitment has been difficult to maintain for reasons that go beyond the engineering. Some of those reasons are geopolitical, rooted in the specific history of this region, and the complicated relationship between the nations that have the most direct interest in exploring it. That is where the story goes next. The story of how humans first tried to understand the Kuril-Kamchatka Trench begins not with a private foundation or an international consortium, but with a single Soviet research vessel and a program of ocean science that was, in its way, one of the most ambitious undertaken by any nation in the 20th century. The ship was called the Vityaz. The name translates roughly as knight or warrior in Russian, and it was a fitting name for a vessel that spent years working in some of the most difficult ocean conditions on Earth. The Vityaz was a converted German ship, the Mars, originally built in 1939, that was transferred to the Soviet Union as war reparations after World War II and redesigned as a dedicated oceanographic research vessel. She entered service with the Soviet Academy of Sciences in 1949, and over the following decade she became one of the most productive research ships in the history of oceanography, not just in this region, globally. Her expeditions ranged across the Pacific, the Indian Ocean, and into the far north and south. But it was her work in the northwestern Pacific, and specifically her work in the Kuril-Kamchatka Trench, that produced some of her most significant scientific results. In 1953, during one of her early Pacific expeditions, Vityaz scientists conducted depth soundings in the trench and recorded a measurement that placed the deepest point at approximately 10,542 meters. That point was subsequently named the Vityaz Deep, and for a period it was believed to be the deepest known location in any ocean, deeper at that time than the confirmed measurements of the Challenger Deep in the Mariana Trench. Later surveys revised the comparison, and the Challenger Deep is now recognised as the deeper of the two, but the Vityaz Deep remains one of the deepest confirmed points on Earth, and the measurement made by that Soviet expedition in 1953 was a genuine scientific achievement. What makes the Vityaz program interesting, though, is not just the depth sounding. The ship returned to the Kuril-Kamchatka Trench multiple times through the 1950s and into the 1960s, and the work done on those expeditions went well beyond simple bathymetry. Soviet scientists aboard the Vityaz collected sediment cores from the trench floor, gathered biological samples using trawls and grab samplers lowered on long wire cables, and compiled detailed records of water temperature, salinity, and current structure at various depths throughout the trench system. This was painstaking, time-consuming work done with equipment that was technically impressive for its era, but would look extremely primitive by modern standards. The wire cable systems used for deep sampling were heavy, slow, and prone to failure. A single deployment to full depth and back could take many hours. The instruments attached to the wire were mechanical, not electronic. Data was recorded on paper or photographic film. And yet the results were real. The samples came back. The measurements were made. Among the most significant findings from the Vityaz expeditions was biological. Before the Soviet work in the Kuril-Kamchatka Trench, and in other deep Pacific trenches, there was genuine scientific uncertainty about whether life could exist at Hadal depths, below 6,000 meters, in the crushing pressure and near-freezing darkness of the deepest ocean. Some researchers believed that the pressure alone would be prohibitive for complex animal life. The Vityaz expeditions helped put that uncertainty to rest. Biological samples brought up from the Kuril Kamchatka Trench contained polychaete worms, segmented marine worms that are common in shallower ocean environments, but were not expected to survive at 10,000 meters. They also contained holothurians, the sea cucumbers, which turned out to be remarkably well adapted to Hadal conditions and would later be recognized as among the most abundant megafauna at extreme depths. Amphipods, small crustaceans, shrimp-like in appearance, were also present in significant numbers. The discovery of these organisms at Hadal depths was not a minor footnote. It fundamentally changed the scientific understanding of where life could exist on this planet, and it raised immediate questions about how these animals were surviving, what they were eating, how they were reproducing, how their physiology was managing pressures that would kill surface-dwelling animals instantly. Those questions are still being actively studied today. The Vityaz scientists who first pulled those samples up from the Kuril-Kamchatka Trench in the 1950s were, without fully realizing it at the time, opening a field of biology that would eventually become known as Hadal ecology. It is worth noting the context in which all of this was happening. The Soviet oceanographic program of the 1950s and 1960s was not purely motivated by scientific curiosity, though genuine curiosity was certainly present among the researchers involved. It was also part of a broader Cold War dynamic in which the Soviet Union and the United States were competing across virtually every domain of science and technology, and the oceans were no exception. Understanding the deep ocean had military implications: submarine warfare, acoustic detection, understanding how sound travelled through deep water, and the Soviet government was willing to fund sustained ocean research programs in a way that might have been harder to justify on purely scientific grounds alone. The Vityaz expeditions benefited from that political context. The ship was well funded, well crewed, and sent out repeatedly over many years. The data accumulated. The Vityaz herself had a long career. She conducted over 60 expeditions over the course of her active service life, covering enormous distances and contributing to scientific knowledge across many ocean regions. When she was finally retired from active research duty in the late 1970s, she was preserved as a museum ship in Kaliningrad, where she still sits today. There is something quietly affecting about that. A ship that spent decades in some of the most remote and difficult ocean environments on Earth, now sitting in a harbour, her hull repainted, and her decks open to visitors who may or may not know what she actually did. But the Vityaz program, as remarkable as it was, had limits that were inherent to the technology of the era. The sampling methods used, wire-lowered grabs, trawls, mechanical sediment corers, were capable of bringing material up from depth, but they were not capable of observing the trench environment directly. There were no cameras that could operate at 10,000 meters in the 1950s and 1960s, not in any practical deployable form. There were no remotely operated vehicles. There were no autonomous instruments that could sit on the trench floor and record data over time. The Soviet scientists knew what they could pull up from the trench in a sample jar, but they had no way of seeing the environment those samples came from. The trench floor remained visually unknown. What it looked like, the actual physical landscape of the Vityaz Deep and the surrounding Hadal Plain, was not something the Vityaz program could tell them. This is a limitation that is easy to underestimate. A biological sample tells you that a polychaete worm can survive at 10,000 meters. It does not tell you how that worm behaves, what it eats in practice, how it moves across the sediment surface, how it interacts with other organisms, or how it responds to disturbance. A sediment core tells you about the material composition of the trench floor at a specific point. It does not tell you about the topography surrounding that point, the current patterns moving across the sediment surface, or the visual texture of the environment. Direct observation, the ability to actually see what is happening at depth, in real time, is a different category of knowledge from sample-based science, and it was entirely beyond the reach of the Vityaz program. The Soviet oceanographic establishment was aware of this gap, and there were ambitions to develop submersible technology that could address it. Soviet engineers did work on deep submersibles during the Cold War era, and some limited work was done. But the full depth capability needed to reach the Vityaz deep, 10,500 meters, was never achieved by Soviet submersible programs in operational form. The deepest the Soviet program got with crewed submersibles was significantly shallower than that. The Kuril-Kamchatka Trench remained, even in the most productive era of Soviet ocean science, a place that could be sampled but not seen. Then the Soviet Union collapsed. And what happened to the oceanographic program in the years that followed was, by most accounts, quite difficult. The dissolution of the Soviet Union in 1991 brought an abrupt end to the institutional infrastructure that had supported the Vityaz expeditions and the broader Soviet ocean science program. Research funding fell sharply. Ships that had been maintained and operated by the state were suddenly underfunded, aging, and in some cases laid up. The Shirshov Institute of Oceanology, the primary Soviet institution for ocean research and the organization that had operated the Vityaz, continued to exist as a Russian institution, but its budget through the 1990s was a fraction of what it had been in the Soviet era. Researchers who had spent careers working on deep-sea programs found themselves in institutions that could no longer support regular expeditions. Some left the field, some left the country. The practical result was that the sustained, repeated program of Kuril-Kamchatka Trench research that had characterized the Vityaz era simply stopped. There were no annual expeditions. There was no continuing program of sediment coring and biological sampling. The data collected by the Vityaz expeditions remained valuable. It is still cited in scientific literature today, but it was not being added to. The trench was being studied by analysing old samples and old records, not by going back. This is a strange kind of scientific situation. The most detailed body of knowledge about the Kuril-Kamchatka Trench that exists was largely assembled in the 1950s and 1960s, using technology that is now more than half a century old, by a scientific program that no longer exists in its original form. The researchers who conducted those expeditions are, for the most part, no longer alive. The institutional memory of that program has been partially preserved in published papers and archived data, but the living knowledge, the practical expertise of people who had actually worked in that trench system repeatedly over many years, has largely dispersed. What this means for the current state of knowledge is not that we know nothing about the Kuril-Kamchatka Trench. The Soviet-era data provides a real foundation, but it is a foundation with significant gaps, and some of those gaps correspond to exactly the kinds of questions that modern ocean science most wants to answer. Questions about hadal ecology, about sediment records of prehistoric earthquakes, about the deep microbial communities that may exist in trench sediments, about the physical oceanography of the hadal zone. These are questions that the Vityaz program was not equipped to address, and that have not been systematically addressed since. Russian oceanographic capacity has partially recovered since the lowest point of the 1990s. The Shirshov Institute has conducted expeditions in more recent decades, and there have been periodic Russian cruises to the Kuril-Kamchatka region. But the scale of activity has never returned to what it was in the Soviet era, and the specific deep sampling infrastructure, the specialized equipment needed to work at full hadal depth, has not been fully rebuilt. The ships exist. The scientists exist. The institutional will to do the work exists. But the sustained funding and the specialized equipment needed to do it systematically at 10,000 meters have remained elusive. There is also a complication that goes beyond funding and equipment, one that has shaped the political environment around this trench in ways that have made international scientific collaboration significantly harder than it might otherwise be. The Kuril-Kamchatka Trench does not exist in a politically neutral space. It sits in a region whose ownership and access rights have been contested for decades, and that contestation has had direct consequences for who can conduct science there, under what conditions, and with what level of cooperation from the nations involved. That layer of the story, the political geography of this trench, is where things get genuinely complicated, and it is a dimension of the exploration problem that no amount of better technology can solve on its own. The Kuril Islands stretch in a long curved chain from the northeastern tip of Hokkaido, Japan's northernmost main island, all the way up to the southern tip of Kamchatka. There are roughly 50 islands in the chain, depending on how you count the smaller ones, and they run for about 1,300 kilometers across some of the most turbulent water in the northern Pacific. Volcanically active, often fog-bound, frequently shaken by earthquakes, they are not comfortable places to live. But they are strategically significant places, and they have been understood as such by more than one nation for well over a century. The dispute over the Kuril Islands is, in its simplest form, a disagreement between Russia and Japan about who owns the 4 southernmost islands in the chain. Those 4 islands, Iturup, Kunashir, Shikotan, and the Habomai group, are referred to in Japan as the Northern Territories, and Japan has maintained a claim to them since the end of World War II. Russia, and before it the Soviet Union, has controlled all 4 islands since Soviet forces occupied them in August 1945, in the final days of the war. The Soviet Union and Japan never signed a formal peace treaty after World War II. Russia and Japan have still not signed one. This means that the two countries are, in the most technical sense, still in a state of unresolved post-war status with respect to these islands, which is a remarkable fact when you consider that the war ended nearly 80 years ago. The history of how this situation came about is genuinely complicated, involving the 1855 Treaty of Shimoda, the 1875 Treaty of St. Petersburg, the 1905 Treaty of Portsmouth after the Russo-Japanese War, the wartime agreements at Yalta in 1945, and the competing interpretations that both sides have applied to each of these documents ever since. Japan argues that the 4 southernmost islands were never part of the Kuril chain, as defined in the agreements that transferred the Kurils to the Soviet Union, and therefore were never legitimately transferred. Russia argues that the post-war settlement was clear and final, and that the islands are Russian territory. Neither side has moved significantly from these positions in decades, despite periodic diplomatic efforts, economic incentive discussions, and summit meetings between Japanese and Russian leaders. What does this have to do with the deep-sea trench? Quite a lot, as it turns out. The Kuril-Kamchatka Trench runs along the eastern side of the Kuril Island chain. Scientific access to the trench, and to the waters immediately surrounding it, is shaped directly by the political environment of the islands above. Research vessels operating in the northwestern Pacific near the Kurils are operating in waters where Russian and Japanese interests overlap in a contested and sometimes tense way. Foreign research ships, including Japanese ships, which would be among the most capable and most motivated to work in this trench, require permission from Russian authorities to operate in certain zones near the islands. That permission is not always easy to obtain. It is sometimes delayed. It is sometimes denied. And the broader diplomatic climate between Russia and Japan at any given moment has a direct effect on how cooperative or uncooperative the process of obtaining that permission tends to be. This is not a hypothetical friction. There have been specific periods when Japanese-Russian scientific cooperation in this region was significantly constrained by the political dispute. Japanese fishing vessels have historically operated in waters near the southern Kurils under complex bilateral arrangements, and disputes over fishing rights have periodically escalated into confrontations that affected the broader climate for cooperation in the region. The territorial dispute tends to infect adjacent areas of the relationship, and scientific access is one of them. It is worth being careful about how this is described, because the situation is not simply that Russia refuses all foreign science in this region. There have been joint Russian-Japanese scientific expeditions, and some cooperation has occurred. The Shirshov Institute and Japanese institutions, including JAMSTEC, have worked together at various points. But the cooperation has been episodic rather than sustained, shaped by the political weather of the moment rather than by a stable framework that would allow long-term scientific planning. Planning a major deep-sea expedition takes years. You need to design and build equipment, arrange ship time, obtain permits, train personnel, and coordinate logistics across multiple institutions. If the political environment can change between when you begin planning and when you actually try to execute the expedition, that uncertainty has real effects on what gets attempted and what gets quietly shelved. There is also the matter of the Sea of Okhotsk, which lies on the western side of the Kuril island chain. The Sea of Okhotsk is almost entirely enclosed by Russian and Japanese territory, and Russia has historically treated it as a zone of particular strategic sensitivity. During the Cold War, Soviet submarine operations in the Sea of Okhotsk were extensive, and the sea was understood by both superpowers as an important area for submarine-launched ballistic missile operations. American submarine intelligence collection in the Sea of Okhotsk, some of which became publicly known through the Operation Ivy Bell story, involving the tapping of Soviet underwater communication cables, illustrated just how militarily charged this region was during the Cold War decades. The military sensitivity of the waters around the Kuril Islands and Kamchatka did not disappear when the Cold War ended. It diminished, but it did not disappear. Kamchatka itself remains a significant Russian military region. Petropavlovsk-Kamchatsky, the largest city on the peninsula and the nearest major port to the northern reaches of the trench, is home to Russian Pacific Fleet submarine infrastructure. The peninsula's eastern coast, which faces the trench, is not heavily populated or developed, but it is not an open, unmonitored coastline either. Foreign vessels operating in waters off Kamchatka are operating in an environment where Russian military awareness is present in a way that it simply is not in, say, the Central Pacific or the Indian Ocean. None of this means that science cannot happen here. It does happen, but it means that every international expedition to this trench has to navigate a layer of political and military sensitivity that adds complexity, time, and uncertainty to the planning process. A research program that might be straightforwardly organised in a politically neutral ocean region requires diplomatic groundwork, bilateral agreements, and careful management of relationships when it happens near the Kuril-Kamchatka Trench. And when those diplomatic relationships deteriorate, as Russian-Japanese relations have done at various points, and as broader Russian relations with Western scientific institutions have also done at various points, the science either slows down or stops. There is a particular irony in this, which is that the nations with the greatest scientific motivation to study the Kuril-Kamchatka Trench are also the nations most directly affected by the geological processes that the trench drives. Japan sits at the intersection of multiple tectonic plates and experiences more significant earthquakes per year than almost any other nation on Earth. The subduction zone that created the Kuril-Kamchatka Trench is the same kind of system that produced the 2011 Tohoku earthquake and tsunami, which killed nearly 20,000 people and triggered the Fukushima nuclear disaster. Understanding the mechanics of subduction zones, how stress accumulates, how it releases, what patterns precede large ruptures, is not an abstract scientific interest for Japan. It is a direct public safety concern. The sediment record in the Kuril-Kamchatka Trench contains information about prehistoric earthquake sequences that could contribute to better understanding of recurrence intervals and rupture patterns in this system. Japanese scientists are very aware of this. The motivation to study this trench is genuine and urgent, not merely academic. And yet the political situation means that the nation with the strongest scientific and practical motivation to conduct sustained research in this trench is also the nation with the most complicated relationship with the country that controls access to it. This is one of those situations where the logic of science and the logic of geopolitics simply do not align, and the result is that important work gets delayed or goes undone. It is also worth noting that the dispute itself shows no signs of resolution in the near term. There have been moments of cautious optimism, periods when Japanese and Russian leaders have suggested that a peace treaty might be achievable, that the island dispute might be managed if not fully resolved. Former Japanese Prime Minister Shinzo Abe pursued extensive personal diplomacy with Vladimir Putin over many years, and there were periods when it seemed possible that some kind of framework agreement might emerge. But those efforts did not produce a resolution, and the broader deterioration of Russian relations with the international community following the 2022 invasion of Ukraine has made the diplomatic environment significantly more difficult. Scientific cooperation between Russian institutions and institutions in Japan and other Western countries has been affected by this deterioration in ways that go beyond the specific Kuril dispute. This is not a small thing for deep-sea science. The community of researchers who work at Hadal depths, the deepest ocean zones below 6,000 meters, is not large. There are not hundreds of institutions around the world with the capability to conduct full-depth research in places like the Kuril Kamchatka Trench. The expertise and the equipment are concentrated in a relatively small number of places, primarily in Japan, the United States, and a few European institutions, along with Russian institutions. When political circumstances reduce the ability of these communities to collaborate and share access, the scientific loss is real and measurable. Expeditions that might have combined Russian geographic access with Japanese technological capability and international scientific expertise simply do not happen in the way they could. There is also a practical dimension to the access question that is easy to overlook, which is the matter of research permits and bureaucratic process even in the best political circumstances. Conducting scientific research in the exclusive economic zone of another country requires formal permission from that country's relevant authorities. For a region like the Kuril-Kamchatka area, where the EEZ boundaries are themselves complicated by the territorial dispute, the question of whose permission is required and through what process is not always straightforward. Russian authorities have jurisdiction over the waters they control, but the specific mechanisms for obtaining research permits, the timelines involved, the documentation required, and the conditions attached to permits can all vary significantly depending on the political moment and the institutional relationships involved. For a deep-sea expedition that requires months of advance planning and cannot easily be rescheduled, permit uncertainty is a serious operational problem. Some researchers have described the experience of planning expeditions to politically sensitive ocean regions as requiring a kind of parallel diplomatic effort that runs alongside the scientific and logistical planning, and that is often more unpredictable than either. You can model the weather statistics for a region and estimate your chances of getting a usable weather window. You cannot easily model the likelihood that a permit application will be processed in time, or that a bilateral scientific agreement will still be in effect when your ship is ready to sail. This unpredictability has a chilling effect on long-term planning. Institutions and funding bodies are less willing to commit resources to expeditions whose political access is uncertain, which means that some of the most scientifically valuable work in politically sensitive regions simply does not get funded in the first place. What all of this means, in practical terms, is that the Kuril-Kamchatka Trench exists in a kind of double remoteness. There is the physical remoteness, the distance from ports, the depth of the water, the severity of the weather, the pressure and darkness at the bottom. And then there is this political remoteness, which is in some ways harder to address because it is not a problem that better engineering can solve. You can build a more capable ROV. You can design a more pressure-resistant housing. You can improve acoustic communication systems. You cannot engineer your way around a territorial dispute that has been unresolved for nearly 80 years, or around the military sensitivity of a region that has been strategically important to a major power for generations. It is a strange situation to sit with. The trench does not know about any of this. The Hadal amphipods moving across the sediment floor at 10,000 meters are entirely indifferent to the question of which nation's flag flies over Uturup. The turbidite layers in the trench sediments, recording earthquakes that happened centuries before Russia and Japan even existed as modern states, are not waiting for a peace treaty before they yield their information. The biology and geology of the trench proceed on their own timescales, completely independent of human political arrangements. But the human capacity to access and study that biology and geology is profoundly shaped by those arrangements in ways that are sometimes frustrating to contemplate. The political dimension of the Kuril-Kamchatka Trench exploration problem is not the only complication, and it is not even the most fundamental one in purely technical terms, but it is a complication that distinguishes this trench from other deep places in the ocean that are equally remote and equally challenging physically. The Kamchatka Trench in the southwestern Pacific is deep and difficult to reach, but it sits in politically uncomplicated waters near New Zealand. The Tonga Trench is similarly challenging and similarly open to international research. The Kuril-Kamchatka Trench is deep, geologically violent, covered by severe weather, and politically restricted all at once. Each of these factors would be a significant obstacle on its own. Together, they create something more than the sum of their parts. And the surface world above the trench, the actual ocean that research ships must cross to get there, the weather systems that bear down on this part of the Pacific for much of the year, adds yet another layer to the challenge. Because even if a research vessel has all its permits in order, all its equipment functioning, and a scientific team ready to work, it still has to physically get to the site and stay there long enough to do something useful. And the ocean above the Kuril-Kamchatka Trench does not make that easy. The northwestern Pacific, in the stretch of ocean that runs along the Kuril Islands and the Kamchatka Peninsula, is not a place that offers much hospitality to ships. It never really has. The sailors and fishermen who have worked these waters for centuries understood this in a practical, immediate way. Not as an abstract meteorological fact, but as something you feel in your body when the weather changes and the swells start building from the northwest. This part of the ocean is genuinely one of the most storm-prone regions on the entire planet, and that is not an exaggeration made for effect. The atmospheric dynamics here are specific and relentless, and they create surface conditions that would be a serious problem for any vessel, let alone a research ship trying to conduct precise scientific operations in a fixed location for days at a time. To understand why the weather here is so severe, it helps to think about what is happening in the atmosphere above this region. The northwestern Pacific sits at the meeting point of two major pressure systems. To the north and west, over the Asian continent, sits the Siberian High, a massive cold, dense air mass that builds over Siberia during the winter months and pushes outward toward the ocean. To the east and south, over the Aleutian Islands, sits the Aleutian Low, a semi-permanent area of low pressure that acts as a kind of storm factory, generating and steering cyclonic weather systems across the northern Pacific. When these two systems interact, and they interact constantly, especially from October through April, the result is a pattern of intense, frequent storms that move through the Kuril and Kamchatka region with remarkable regularity. Winter wave heights in this area routinely reach 8 to 12 meters. Not occasionally, not in exceptional circumstances, routinely. A 12-meter wave is roughly the height of a 4-story building, and it is moving. Research vessels operating in these waters during winter months face conditions that would be considered extreme in most other ocean regions. Even in summer, when the pressure gradient between the Siberian High and the Aleutian Low weakens somewhat, the region remains prone to rapid weather deterioration. Storms can develop or intensify faster than forecasting models can reliably predict, which means that weather windows, those stretches of relatively calm conditions that deep-sea operations depend on, are not only rare, but also harder to trust. You might have a forecast showing 3 days of acceptable conditions and have that window close after 36 hours because a system developed more quickly than expected. Fog is another persistent problem that gets less attention than the dramatic wave heights, but causes its own operational difficulties. The Kuril region is foggy for a substantial portion of the year, particularly in late spring and summer, when warmer, moister air moves over the still cold surface water and condenses. dense fog limits visibility to the point where it affects navigation, complicates helicopter operations if a ship is working with rotary wing support, and creates general operational uncertainty. There is something almost ironic about the fact that the summer months, which offer somewhat reduced storm activity compared to winter, bring their own persistent problem in the form of fog. The ocean here seems to resist straightforward access in multiple ways simultaneously. Then there is the matter of simply getting to the site. The nearest major port to the southern Kuril Trench area is Petropavlovsk-Kamchatsky, which sits on the eastern coast of the Kamchatka Peninsula. It is a significant port by the standards of this remote part of the world, with facilities that can support oceanographic research vessels, but it's not close to the southern end of the trench in any convenient sense. The distance from Petropavlovsk-Kamchatsky to the southern portions of the Kuril-Kamchatka Trench, the areas near the deepest measured points, is roughly 1,000 kilometers. For a research vessel travelling at 12 to 15 knots, that is several days of transit each way. And those transit days are not spent in protected waters. The ship is crossing open ocean in one of the stormiest regions on Earth, burning fuel, experiencing mechanical wear, and consuming the time and energy of the scientific crew before they have even arrived at the research site. This transit problem matters more than it might initially seem. Deep-sea research expeditions are planned around total ship time, which is expensive and finite. A vessel might be allocated 30 days for an expedition. If 4 or 5 days each way are consumed by transit from the nearest port, and if the ship loses additional days waiting at anchor for weather windows to open, the actual time available for scientific operations at the trench site can shrink dramatically. There have been expeditions to difficult ocean regions where the productive scientific time on site amounted to a fraction of the total expedition duration, simply because transit and weather consumed everything else. The Kuril-Kamchatka region is particularly vulnerable to this kind of time erosion. Ice adds another complication to the northern approaches. The Sea of Okhotsk, which lies to the west of the Kuril Islands, develops significant sea ice during winter months. It is the southernmost sea in the northern hemisphere to form substantial seasonal ice cover, which reflects just how cold this region gets. The northern portions of the trench system, near the Kamchatka Peninsula, can be affected by ice conditions that limit vessel access during the coldest months. Research ships operating here in winter need to be ice-strengthened or ice-capable, which further narrows the pool of suitable vessels. Standard oceanographic research vessels without ice reinforcements simply cannot safely operate in some of these northern approaches during winter, which means that certain parts of the trench system are effectively inaccessible for months at a time, regardless of scientific interest or funding availability. What makes all of this particularly consequential for deep-sea operations specifically is the requirement for sustained, stable surface conditions. Deploying deep-sea equipment, ROVs, landers, sediment corers, acoustic instruments, requires a ship to maintain a relatively stable position for extended periods. Modern research vessels use dynamic positioning systems, which use GPS and thruster arrays to hold the ship in place without anchoring, but these systems have limits. In heavy seas, dynamic positioning becomes increasingly difficult to maintain, and the vessel's motion transfers through any tethered equipment to the instruments below. A ship rolling and heaving in a 3-meter swell creates movement at the surface that, transmitted down a cable, can damage equipment or compromise the precision of operations thousands of meters below. The deeper the operation, the longer the cable, and the more that surface motion is amplified and complicated by the dynamics of the cable itself. For full-depth operations at 10,000 meters or more, the requirement for calm surface conditions is not a preference. It is a hard operational constraint. Deploying and recovering equipment at those depths takes many hours. A lander dropped to 10,000 meters and left to soak for a scientific collection period might need 12 to 16 hours of total deployment time. During that entire window, the ship needs to maintain its position, the weather needs to stay within acceptable limits, and nothing mechanical can go wrong with the recovery system. In a region where weather windows of 2 to 3 consecutive calm days are genuinely rare, finding a window that is both long enough and actually arrives when the ship is on site is a significant logistical challenge. Researchers planning expeditions to the Kuril-Kamchatka Trench have to build weather contingency into their plans in ways that expeditions to more sheltered or climatically stable ocean regions do not. There is also the question of what happens when weather deteriorates unexpectedly during an operation. If a ship is in the middle of recovering a deep-sea instrument and conditions worsen suddenly, the crew faces difficult decisions about how aggressively to push the recovery before the sea state makes it unsafe. Equipment that cannot be recovered quickly enough may have to be abandoned, or the recovery may be attempted in conditions that risk damaging both the instrument and the ship. The loss of the Jamstek ROV Kaiko in 2003, which will come up in more detail later in this story, involved a cable failure during recovery operations, and while the specific circumstances were their own, the general vulnerability of deep-sea equipment during the surface interface of deployment and recovery is a real and recurring concern. The surface conditions above the Kuril-Kamchatka Trench make this vulnerability more acute than it would be in calmer waters. It is worth pausing to let this accumulate for a moment. We're talking about a research ship that has travelled 1,000 kilometres through open ocean in one of the world's stormiest regions, has navigated permit and access requirements, has arrived on site with its crew and equipment intact, and now needs to find a stretch of calm weather long enough to actually deploy instruments to 10,000 metres and recover them successfully. And it needs to do this while burning fuel, managing crew fatigue, and holding the ship in position with dynamic positioning systems in waters where the weather can change within hours. This is before any of the actual deep-sea challenges, the pressure, the darkness, the technical demands of operating at Hadal depths, have even entered the picture. The surface world above the trench is its own obstacle course. Some researchers who have worked in this region describe the experience of waiting for weather windows as one of the defining features of the work. You're anchored, or drifting in a holding pattern, watching forecast models update every 6 hours, trying to judge whether the window that looks promising on the screen will actually materialise and hold long enough to be useful. There is a particular kind of patience required by this kind of science that is different from the patience of laboratory work or theoretical modelling. It is a patience that involves physical discomfort. Ships at anchor in open ocean are not still, even in moderate conditions, and genuine uncertainty about whether the work you have travelled so far to do will actually be possible before your ship time runs out. The people who conduct this kind of research are not, as a rule, people who complain about it. There is a culture in deep-sea oceanography of accepting the conditions as part of the work, of building contingency into plans and then accepting what the ocean allows. But even within that culture, the Kuril-Kamchatka region is understood to be particularly demanding. The combination of distance from port, frequency and severity of storms, fog, ice in the northern approaches, and the specific operational requirements of Hadal depth work makes this one of the more difficult surface environments in which to conduct deep-sea science anywhere in the world. And there is a compounding effect worth noting. The logistical difficulty of operating in these surface conditions means that expeditions to this trench are relatively rare, which means that when an expedition does succeed in getting to site and deploying equipment, the pressure to make every deployment count is enormous. There is less opportunity to repeat a failed deployment, less margin for equipment problems, less tolerance for the kind of iterative trial and error that accelerates learning in more accessible research environments. Each successful operation in the Kuril-Kamchatka Trench represents a concentration of effort, expense, and good fortune that is difficult to replicate quickly. When something goes wrong, and in deep-sea work, things do go wrong. The cost is not just the immediate loss of equipment or data. It is the loss of one of a very small number of opportunities to learn anything at all about this place. The surface conditions, in this sense, are not just a physical obstacle. They shape the entire character of the scientific knowledge that exists about this trench. The data that has been collected here is sparse, partly because the trench is deep and the technology is limited, but also because the weather makes access genuinely difficult on a consistent basis. Every data set from this region carries within it the implicit story of the conditions under which it was obtained. The weather windows seized, the transits endured, the deployments attempted in marginal conditions because there was no better opportunity available. The trench sits beneath all of this, patient and indifferent, while the surface world above it does its best to keep human curiosity at a distance. And yet, despite all of this, the storms, the fog, the ice, the distance, the weather windows that open and close before they can be fully used, researchers have found ways to reach this place and bring back something from it. The equipment they use when they finally get there, and the specific technical challenges of operating at full ocean depth, represent yet another set of constraints that are worth understanding carefully. So let us talk about the tools, because even when a ship has made the transit, even when the weather has cooperated, even when the permits are in order, and the crew is ready and the forecast looks promising for the next 36 hours, the question of what you actually lower into 10,000 meters of water is its own deeply complicated subject. The first thing to understand is how few instruments exist in the world that are capable of reaching full ocean depth in a trench like this one. Full ocean depth, in this context, means roughly 10,500 meters, the approximate depth of the Vityaz Deep at the southern end of the Kuril Kamchatka Trench. That number matters because it sets a hard engineering threshold. An instrument rated to 8,000 meters will not survive at 10,000. The pressure difference between those two depths is not trivial. It is the difference between approximately 800 atmospheres and over 1,000, and pressure at these depths does not forgive engineering margins that were calculated for shallower water. Equipment that has worked reliably at 9,000 meters has failed catastrophically at 10,000. The trench does not offer partial credit. As of the early 2020s, the number of remotely operated vehicles in the world capable of operating at full ocean depth, meaning 10,500 meters or deeper, could be counted on one hand with fingers to spare. This is not a figure that improves quickly. Building a full ocean depth ROV is an enormously expensive and technically demanding undertaking. The pressure housings must be engineered to tolerate forces that would crush standard titanium spheres. The thrusters, cameras, manipulator arms and electronic systems must all be individually rated and tested for conditions that cannot be fully replicated in any laboratory on land. The syntactic foam that provides buoyancy must maintain its structural integrity under pressures that compress most materials measurably. The tether or umbilical connecting the vehicle to the surface ship must be kilometers long, strong enough to handle the mechanical loads of deployment and recovery in open ocean, and capable of transmitting data and power over that entire distance without failure. Every component of a full ocean depth ROV represents a separate engineering problem that must be solved before the vehicle can be trusted to descend. The Jamstek ROV Kaiko is one of the most important examples in this story. Kaiko was a Japanese vehicle, operated by the Japan Agency for Marine Earth Science and Technology, and it was one of the most capable deep-sea ROVs ever built. In 1995, Kaiko reached the bottom of the Challenger Deep in the Mariana Trench, the deepest point in any ocean, and it conducted scientific work in several of the world's major trenches during the following years. It was, by any measure, a remarkable piece of engineering and a genuinely important scientific instrument. In May 2003, during operations near the Mariana Trench, Kaiko was lost. The secondary cable connecting the ROV to its launcher vehicle parted during recovery operations, and Kaiko sank to the bottom of the ocean. It was never recovered. The loss was not the result of a pressure failure or a deep-sea malfunction. It happened at the surface interface, during the mechanical process of bringing the vehicle back aboard the ship, in conditions that were not extreme by the standards of that region. The cable simply failed at the wrong moment, and one of the world's most capable scientific instruments was gone. Jamstek eventually developed a replacement vehicle, the Kaiko Mark IV and later the Abysmo system, but the loss of the original Kaiko represented a significant setback to deep-sea exploration capability that took years to partially recover from. The story of the Nereus ROV is in some ways even more striking. Nereus was developed by the Woods Hole Oceanographic Institution in the United States, and it represented a different design philosophy from traditional ROVs. Rather than using a heavy umbilical tether, Nereus was designed to operate as a hybrid vehicle. It could function either as a free-swimming autonomous underwater vehicle, or, when connected to a very thin fibre-optic tether, as a remotely operated vehicle. This design made it lighter and more manoeuvrable than conventional ROVs, and it allowed the surface ship to maintain a less rigid mechanical connection to the vehicle during operations. Nereus successfully reached the bottom of the Challenger Deep in 2009, making it one of only a handful of vehicles to have done so. It conducted work in several other deep trenches in the following years. In May 2014, during a dive in the Kamchatka Trench northeast of New Zealand, at a depth of approximately 9,990 metres, Nereus imploded. The vehicle simply ceased to exist as a functional object. The pressure at that depth, just barely short of 10,000 metres, overcame the structural integrity of some component, and the implosion destroyed the vehicle. Pieces of foam and debris floated to the surface. The data and samples it had been collecting were lost with it. Nereus was irreplaceable in the short term, and its loss left a significant gap in the world's full ocean depth exploration capability. These are not cautionary tales told to be dramatic. They're concrete illustrations of the fragility of the instruments that are supposed to explore places like the Kuril Kamchatka Trench. When there are fewer than 5 vehicles in the world capable of reaching full ocean depth, and when 2 of the most capable ones were lost within roughly a decade of each other, one to a cable failure, one to an implosion, the arithmetic of deep-sea exploration becomes very stark. Each surviving vehicle is irreplaceable in any practical time frame. Each dive represents an exposure of an extraordinarily valuable and difficult-to-replace instrument to conditions that have already destroyed similar instruments. The scientists and engineers who operate these vehicles are careful, experienced, and thoughtful about risk. But the risks are real, and the consequences of losing a full ocean-depth ROV extend far beyond a single expedition. They affect the global capacity for Hadal science for years. One alternative to ROVs that has seen more use in the Kuril Kamchatka Trench is the lander, a free-falling instrument platform that descends to the bottom under its own weight, conducts observations or collects samples, and then releases a ballast weight to ascend back to the surface. Landers have some genuine advantages. They do not require a tether, which eliminates one of the major failure points that destroyed Kaiko. They are mechanically simpler than ROVs, which makes them somewhat less expensive to build and operate. They can be built to carry bait cameras that attract and photograph the animals that come to investigate a food source, which has produced some of the most striking biological footage ever obtained from Hadal depths. Landers have been deployed in the Kuril Kamchatka Trench system, and some of the biological observations discussed later in this story came from lander deployments. But landers have significant limitations. They cannot navigate. They fall where they are released and land where the bottom topography and current take them. They cannot move to investigate a feature, collect a sample from a specific location, or reposition if they land somewhere scientifically uninteresting. The data they return is limited by what their fixed instruments can observe from a single stationary point on the trench floor. A bait camera on a lander will show you the animals that come to the bait in the vicinity of the landing site, but it cannot tell you what is happening 50 metres away, or whether the community it observes is typical of the trench as a whole or an anomaly of that particular location. Landers are useful and important, but they are not a substitute for a vehicle that can actually move through the water and explore. There is also the question of acoustic communication. In the deep ocean, Sound is the primary medium for transmitting data and commands between the surface and submerged instruments. Light does not penetrate to Hadal depths in any useful form, and electromagnetic signals cannot travel through seawater over any significant distance. Sound travels reasonably well through water, but the acoustic modems used for deep-sea communication are slow by any modern standard. Data transmission rates are typically measured in hundreds of bits per second, not megabits. Sending a high-resolution image from a vehicle at 10,000 meters to the surface ship takes time. Sending a command from the surface to the vehicle and receiving a confirmation takes time. At extreme depths, the round-trip travel time for an acoustic signal, down to 10,000 meters and back, is several seconds. This does not sound like much until you're trying to pilot a vehicle through complex terrain or respond quickly to an unexpected situation. The communication lag is a real operational constraint, and it is one reason that deep-sea ROVs require experienced pilots who can anticipate what the vehicle will need to do rather than simply reacting to what they see on the screen. Multi-beam sonar mapping from surface ships has provided some of the most detailed information about the shape of the Kuril Kamchatka Trench without requiring any instrument to descend into it. Multi-beam systems emit fans of acoustic pulses from the hull of the ship and measure the return time of the echoes to construct detailed three-dimensional maps of the seafloor. Modern multi-beam systems are capable of producing bathymetric data with resolution of tens of meters even at full ocean depth, which is remarkable given that the sound is travelling 5 kilometers or more each way. This kind of mapping has been done in portions of the Kuril Kamchatka Trench, and it has revealed the broad structure of the trench floor, the long axis of the main trough, the ridges and sediment plains along the margins, the fault structures associated with the subduction zone. But bathymetric mapping from the surface tells you about the shape of the bottom, not about what lives there, what the sediment contains, what the water chemistry looks like, or how the biological communities are distributed. It is a map of an outline, not a picture of the interior. The trench is approximately 2,200 kilometers long. Even a highly successful OV expedition that completes several dives over a period of 2 or 3 weeks will cover a distance along the trench floor that is, in any honest accounting, a tiny fraction of the total. A single ROV dive might cover a few kilometers of actual seafloor transect if conditions are favourable and the dive is long. Across the full length of the trench, that represents a sample of less than 1% of the linear extent of the system, and the trench is not uniform across its length. The geology changes, the depth changes, the biological communities almost certainly change. The sediment record at one end of the trench may be quite different from the record at the other end. A handful of successful dives, however scientifically valuable each one is individually, cannot characterize a system of this scale in any comprehensive way. There is something almost paradoxical about it. The technologies that exist to explore the Kuril Kamchatka Trench are the most sophisticated ocean science instruments ever built. The people who design, build and operate them are at the absolute frontier of what human engineering can accomplish in extreme environments. And yet, when you set those instruments against the actual scale and depth of the trench, the gap between what can be done and what would be needed to truly understand this place is enormous. It is not a gap that reflects any failure of effort or imagination. It reflects the genuine difficulty of the problem, the combination of depth, pressure, remoteness, weather, geopolitical access, and sheer physical extent that makes this trench so resistant to exploration. What has been attempted here, and what has been lost in the attempting, carries its own weight. The Kaiko at the bottom of the ocean somewhere near the Mariana Trench, the Nereus in fragments near the Kermadec, expeditions that turned back before reaching site because the weather window closed, landers that descended and returned with footage of animals that had never been photographed before, from a single point on a trench floor that stretches for over 2,000 kilometers. Each of these outcomes, are the losses, the partial successes, the narrow glimpses, represents a real scientific effort that ran up against the specific conditions of Hadal exploration and came away with whatever it could. And yet what has come back, the biological samples, the lander footage, the sediment cores, the acoustic maps, has been genuinely remarkable. Because whatever the trench withholds from the instruments sent to study it, it has not withheld life. The animals that have been found in the Kuril Kamchatka Trench, living at pressures that would destroy most engineered systems, tell a story about biology at the edge of what seems possible, and that story is worth examining closely. The Hadal zone is, by most measures, the least understood biological environment on Earth. Not the least interesting, quite the opposite, but the least understood, simply because reaching it requires such an extraordinary amount of effort, equipment, and luck that the number of times it has been sampled in any rigorous way remains surprisingly small. What has come back from the Kuril Kamchatka Trench specifically is, given those constraints, genuinely remarkable. And the more carefully you look at what has been found there, the more clearly you see how much remains unknown. Start with the amphipods, because they are almost always the first animals mentioned in any discussion of Hadal biology, and for good reason. Amphipods are small crustaceans, distantly related to shrimp and crabs, and they are extraordinarily successful at extreme depths. The species Hirondellea gigas is one of the most commonly collected Hadal organisms in the Western Pacific Trench systems, including the Kuril Kamchatka Trench. They are not large. Adults typically measure somewhere between 2 and 4 centimetres, but they occur in enormous numbers relative to other megafauna at these depths, and they are remarkably effective scavengers. Bait traps lowered into Hadal trenches are typically overwhelmed by amphipods within hours of reaching the bottom. Lander footage from multiple trench systems has shown these animals arriving at bait in dense swarms, sometimes within minutes of the camera beginning to record. Their ability to locate food sources across large distances in complete darkness, using chemoreception, essentially a highly developed sense of smell in water, is one of the more quietly astonishing things about them. What makes Hirondellea gigas particularly interesting from a physiological standpoint is what it has to do to survive at pressures exceeding 1,000 atmospheres. At that pressure, the cell membranes of most organisms would become rigid and dysfunctional. The lipid bilayers that form the walls of cells depend on a certain degree of fluidity to allow proteins to move and function correctly, and extreme pressure compresses those membranes in ways that disrupt normal biochemistry. Hadal amphipods address this partly by incorporating specific types of unsaturated fatty acids into their cell membranes, fatty acids that remain more fluid under high pressure than the saturated fats that dominate the membranes of shallow water species. Some of these fatty acids, interestingly, appear to be obtained directly from the food the amphipods consume, which includes organic material that has sunk from the productive surface waters above. The northwestern Pacific is one of the most biologically productive ocean regions in the world, and the Kuril Kamchatka Trench sits directly beneath it. The organic rain that falls from the surface, dead phytoplankton, zooplankton carcasses, fecal pellets, the occasional larger carcass of a fish or marine mammal, is relatively abundant here compared to trenches beneath oligotrophic or nutrient-poor ocean regions. This matters for the entire Hadal food web, not just the amphipods. Sea cucumbers, or holothurians, are perhaps the most visually distinctive animals that have been observed at full depth in the Kuril Kamchatka Trench. At Hadal depths, certain species of holothurian can dominate the megafauna almost completely, sometimes accounting for the majority of visible animal biomass in lander footage. They move slowly across the sediment surface, processing organic-rich sediment through their digestive systems in a way that is not unlike earthworms processing soil, ingesting sediment at one end, extracting organic material, and depositing processed sediment at the other end. In some areas of the trench floor, the sediment surface is visibly reworked by holothurian activity, covered in the characteristic trails and mounds left by animals moving slowly in the darkness. Some Hadal holothurian species are translucent or nearly so, and they have been photographed drifting slightly above the sediment surface, apparently swimming in a slow, undulating way that looks almost ethereal in the lander footage. There is something about watching that footage, the slow drift of a nearly transparent animal through absolute darkness at 10,000 meters. That is genuinely difficult to put into words. It does not look hostile down there. It looks inhabited. Polychaete worms are another consistent presence in the biological samples collected from this trench system. Polychaetes are segmented worms, and they are among the most diverse and ecologically important groups of animals in the deep sea. In the Kuril Kamchatka Trench, they have been collected from sediment cores and from traps, representing multiple families and feeding strategies. Some are predators or scavengers, others are deposit feeders, processing sediment in the same general way as the holothurians. Some build tubes in the sediment. The diversity of polychaete species at Hadal depths is not fully characterized. The sampling has simply not been extensive enough. But the species that have been identified include some that appear to be restricted to this trench system and do not occur in other Hadal environments. Whether those apparent endemics are truly unique to the Kuril Kamchatka Trench, or whether they also exist in other trenches but have not yet been collected there, is a question that cannot be answered without much more extensive sampling across multiple sites. Foraminifera are single-celled organisms that build intricate shells, or tests, from calcium carbonate or sediment particles, and they are found throughout the deep ocean. In the Hadal zone, they form an important part of the microbial and meiofaunal community, the layer of life that exists within and just above the sediment surface, too small to be captured by most conventional sampling methods, but ecologically critical as a link between the bacterial community and larger organisms. The foraminifera found in Kuril Kamchatka Trench sediments include both living specimens and the accumulated tests of dead individuals, which build up in the sediment over thousands of years and form part of the geological record. Their species composition at different depths and locations within the trench reflects both the physical conditions and the history of the water column above them, making them useful proxies for reconstructing past oceanographic conditions, though that is a subject that connects more directly to the sediment archive story, which deserves its own careful attention. The base of the food web in the trench is bacterial. Bacteria colonize organic particles as they sink through the water column, and by the time those particles reach Hadal depths, they are heavily processed, but they still carry enough organic carbon to support a community. Bacterial biomass in Hadal sediments can be surprisingly high relative to the apparent scarcity of food, partly because bacteria are extraordinarily efficient at extracting energy from low-quality organic material. Archaea, a separate domain of life from bacteria, though superficially similar, are also present in Hadal sediments and are particularly important in nitrogen cycling. The microbial community in the Kuril Kamchatka Trench has not been studied with anything approaching the depth that would be needed to characterize it fully. Metagenomic sampling, collecting environmental DNA and sequencing it to identify what organisms are present without culturing them individually, has transformed deep-sea microbiology in other systems, and there is every reason to think it would reveal a similarly complex and novel community in this trench. But metagenomic work requires samples, and samples require expeditions, and expeditions to this particular trench are rare. One thing that has been observed in lander footage from the Kuril Kamchatka Trench, and from Hadal trenches generally, is bioluminescence. This is worth pausing on for a moment. Bioluminescence, the production of light by living organisms through chemical reactions, is extraordinarily common in this ocean. The majority of deep-sea animals produce some form of bioluminescent light. It is used for communication, for attracting prey, for startling predators, for camouflage against faint downwelling light in the mesopelagic zone. At Hadal depths, where there is no downwelling light to camouflage against, and where the animal density is generally low, bioluminescence takes on different potential functions. It has been observed in Hadal amphipods and in some deep-sea fish species that venture into Hadal depths. The footage from landers in this trench system has captured brief flashes and glows in the surrounding water column during deployments, some of which are attributable to specific animals disturbed by the lander's descent or by the bait, and some of which are harder to explain. The darkness at 10,000 meters is not entirely without light. It is punctuated by the cold chemical glow of organisms that have been producing their own illumination for millions of years, in a place that no human eye has ever directly seen. The question of endemism, of species that exist only in this trench and nowhere else, is one of the more scientifically compelling aspects of Hadal biology, and it is a question that the Kuril-Kamchatka Trench raises in an interesting way. Hadal trenches are geographically isolated from each other. They are separated by mid-ocean ridges, by vast expanses of abyssal plain, by differences in water chemistry and temperature and food availability. This isolation has persisted over geological timescales, which is long enough for significant evolutionary divergence to occur. The amphipods, polychaetes and holothurians found in the Kuril-Kamchatka Trench are not necessarily the same species as those found in the Mariana Trench, or the Tonga Trench, or the Japan Trench, even though all of those environments share broadly similar physical conditions. Some species appear to be shared across multiple trench systems, presumably because their larvae or dispersal stages can travel through the deep water column between trenches over long periods. Others appear to be restricted to single trench systems. Determining which is which requires comparative sampling across multiple trenches, and that kind of systematic comparative work has barely begun for the Kuril-Kamchatka system specifically. There is also the matter of what happens to the trench's biological community when a major earthquake occurs. The Kuril-Kamchatka region generates some of the largest earthquakes on Earth, and those earthquakes do not only affect the surface. When a magnitude 8 or greater event occurs along the subduction zone, the seafloor moves, sediment is disturbed, turbidity currents, underwater avalanches of suspended sediment, can travel down the trench walls and across the trench floor, resuspending organic material, burying sessile organisms, and reorganizing the physical structure of the seafloor over large areas. How the biological community recovers from these events, how long recovery takes, which species are most affected, and whether the community composition shifts in the aftermath are all questions that have not been studied in this trench in any systematic way. In other deep-sea environments, particularly around hydrothermal vents, where disturbance events are more predictable and have been observed multiple times, ecologists have documented succession patterns and recovery timescales. In the Kuril-Kamchatka Trench, the combination of seismic frequency and sampling scarcity means that the relationship between geological disturbance and biological community structure is almost entirely uncharacterized. What has been sampled, when you step back and consider it honestly, is a collection of points. A sediment core here, a lander deployment there, a trawl sample from the 1950s Soviet expeditions, a bait trap recovered with amphipods, a few hundred meters of ROV video footage from a dive that covered a small fraction of a single segment of a trench that runs for over 2,000 kilometers. Each of those data points is scientifically valuable. The species descriptions that have come from those samples, the physiological studies done on the amphipods and holothurians collected here, the genetic work that has identified relationships between Hadal species and different trench systems, all of that represents real scientific progress, carefully achieved by researchers who worked with whatever material they could obtain. But the fraction of the trench that has been biologically sampled in any form is, by any honest estimate, vanishingly small. Estimates of what fraction of the Hadal zone globally has been directly sampled vary, but figures of less than 1% are commonly cited, and the Kuril-Kamchatka Trench, despite its size and depth, is not an exception to that general picture. The scientific stakes of this gap are not abstract. The Hadal zone represents the deepest and most pressure-extreme environment in which complex multicellular life exists on Earth. Understanding how animals survive and function at these depths, what biochemical adaptations they have developed, how their genomes differ from shallow water relatives, how their communities are structured and maintained, has direct relevance to questions about the limits of life, about the mechanisms of pressure adaptation, and potentially about the conditions under which life might exist in other extreme environments, including extraterrestrial ones. The Kuril-Kamchatka Trench is not a scientific curiosity. It is a major biological system that remains largely uncharacterized, in a region of the ocean where the surface productivity is high enough to sustain a substantial hadal community, and where the geological history is complex enough to have produced evolutionary conditions distinct from other trench systems. Every sample that has come up from this trench has contained something worth examining. Every lander deployment has returned footage of animals behaving in ways that raise new questions. The biological story of this trench is not a story of emptiness or sterility. It is a story of life that is stranger and more resilient than almost anything found at the surface, persisting in conditions that seem designed to make persistence impossible, in a darkness that has never been interrupted by sunlight, under pressures that would collapse most of the objects humans use in daily life, in a place that most people have never heard of. What makes that story so frustrating from a scientific perspective is not that the trench refuses to yield information. It is that the information it yields, each time something is sent down and successfully recovered, is so consistently extraordinary that the smallness of the sample feels almost painful. You get a glimpse, and the glimpse is remarkable, and then you realise how much of the picture is still missing. Which is, in a way, what the sediment beneath all of those animals has also been quietly recording. A different kind of archive, laid down over thousands of years, waiting for instruments careful enough to read it without disturbing what makes it valuable. That sediment is worth thinking about carefully because it holds a kind of record that nothing else on Earth can replicate in quite the same way. The floor of the Kuril-Kamchatka Trench accumulates material slowly. Particles drift down from the water column above. Tiny fragments of dead organisms, mineral dust, volcanic ash, the microscopic shells of foraminifera and diatoms that lived and died in the sunlit surface water thousands of meters overhead. In the open ocean, this material settles at rates that can be measured in millimeters per 1,000 years. In a trench environment, the accumulation rate is somewhat higher because the trench geometry funnels material inward from the surrounding sea floor, and because the highly productive surface waters of the northwestern Pacific generate a relatively steady supply of organic particles. But even at elevated rates, the sediment column builds slowly. A core that penetrates 2 or 3 meters into the trench floor may be reading a record that stretches back 10,000 years or more. Some cores from comparable trench environments have yielded records extending back to the last glacial maximum and beyond. What that record contains is not a simple, uniform layer of fine particles. It is a stratigraphy, a sequence of distinct layers, each one representing a different moment or event in the geological and environmental history of the region. And in the Kuril-Kamchatka system, those layers carry information that scientists in several different fields have strong reasons to want. The most immediately legible entries in this archive are the turbidite layers. A turbidite is a layer of coarser sediment deposited rapidly by a turbidity current, one of those underwater avalanches of suspended material that gets triggered when the seafloor is shaken hard enough. When a large earthquake occurs along the subduction zone, it can destabilize sediment that has been accumulating on the trench walls and on the surrounding abyssal plain. That material collapses inward and downward, travelling along the trench floor as a dense, fast-moving current of sediment-laden water before settling out as a distinct layer. The resulting turbidite is different in texture and composition from the background sediment above and below it. Coarser, more poorly sorted, sometimes graded from coarser material at the base to finer material at the top, as the current slows and the particles settle by size. In a sediment core, a turbidite appears as an interruption in the otherwise fine-grained background sequence. It is, in a sense, the physical signature of an earthquake, preserved in the sediment for as long as the sediment remains undisturbed. This is not a theoretical observation. After the 2011 Tohoku earthquake, the magnitude 9.0 event that generated the devastating tsunami and caused the Fukushima nuclear disaster. Researchers who subsequently collected sediment cores from the Japan Trench found a distinct turbidite layer near the top of the sediment column, corresponding to the time of the earthquake. The layer was identifiable, measurable, and interpretable. It confirmed that turbidite stratigraphy can be used as a record of historical earthquake sequences, and it validated the methodology for reading older, deeper layers in the sediment column as evidence of prehistoric earthquakes that occurred long before any human observer was present to record them. The Kuril-Kamchatka Trench sits in a region that has produced some of the largest earthquakes in the instrumental record. The 1952 Severokurilsk earthquake, the 2006 and 2007 Kuril Islands events, and numerous other large subduction zone ruptures over the past century are all documented. But the instrumental record only extends back to the early 20th century, and even the historical record, based on written accounts of tsunamis and ground shaking, reaches back only a few hundred years in this region. Before that, the seismic history of the Kuril-Kamchatka subduction zone is essentially blank, at least from a documentary perspective. The sediment is not blank. The sediment has been recording every major earthquake for thousands of years in the form of turbidite layers stacked one above another in the trench floor, each one waiting to be dated and interpreted. Knowing the prehistoric earthquake history of a subduction zone is not just scientifically interesting in an abstract sense, it has direct practical relevance for understanding the recurrence interval of large events. How often, on average, a magnitude 8 or greater earthquake occurs on a given segment of the fault, and how much time has elapsed since the last one. That information feeds directly into seismic hazard assessments, which in turn inform building codes, tsunami warning systems, and emergency planning for coastal communities across the northern Pacific. The cities and towns along the Kamchatka coast, the Kuril Islands, and the coasts of Japan and Alaska are all downstream, in a sense, from the seismic behaviour of this subduction zone. Every major Kuril-Kamchatka earthquake has the potential to generate a transoceanic tsunami. Understanding the full statistical distribution of these events, not just the last 100 years of instrumental data, but the last several thousand years of sediment record, would meaningfully improve the accuracy of hazard models for millions of people. There are also the ash layers. The Kamchatka Peninsula and the Kuril Islands together form one of the most volcanically active chains on Earth. When a major eruption occurs, it can inject ash into the atmosphere in quantities large enough to be transported hundreds or thousands of kilometers before settling out into the ocean. That ash sinks through the water column and is incorporated into the sediment record as a thin, chemically distinct layer called a tephra. Different volcanic eruptions produce ash with different geochemical signatures, different ratios of trace elements, different mineral compositions, so a tephra layer can often be matched to a specific volcano and, with enough additional analysis, to a specific eruption event. When a tephra layer appears in a sediment core alongside organic material that can be radiocarbon dated, the tephra layer itself becomes dated. And once a tephra layer is dated, it becomes a time marker, a fixed point in the sediment column against which the rates of other processes can be measured. The Kuril-Kamchatka sediment record contains numerous tephra layers because the region has been volcanically active throughout the Holocene and well before. Some of these layers correspond to eruptions that are documented in historical records or in ice cores from Greenland and Antarctica, where volcanic sulfate signals have been detected and dated. Others correspond to eruptions that are not well documented at all, because they occurred before human settlement of the region, or because the historical record from this part of the world is sparse. Correlating tephra layers in the trench sediment with eruption histories reconstructed from the volcanoes themselves is a way of building a more complete picture of volcanic activity in the region over thousands of years, and by extension, of understanding the relationship between volcanic events and the broader environmental and climatic history of the northwestern Pacific. Then there is the organic carbon record. The surface waters above the Kuril-Kamchatka Trench are among the most biologically productive in the world ocean. The northwestern Pacific is a region of strong seasonal upwelling, where cold, nutrient-rich water rises to the surface and fuels dense blooms of phytoplankton each spring and summer. That organic productivity eventually sinks, in the form of dead organisms and fecal pellets and aggregated particles, and a portion of it reaches the trench floor and is incorporated into the sediment. The organic carbon preserved in those sediments carries a record of how surface productivity has changed over time, how the intensity and timing of upwelling has shifted in response to changes in ocean circulation, atmospheric conditions and climate. In periods when the climate was different, during the last glacial maximum, for example, when sea surface temperatures were lower and atmospheric circulation patterns were altered. The biological productivity of the surface ocean was also different, and those differences are recorded in the organic chemistry of the sediment layers deposited during those periods. Reading that record accurately requires sediment that has been preserved in good condition, collected without contamination, and analysed with appropriate techniques. It also requires knowing the age of the sediment at different depths in the core, which is where the tephra layers and other dating methods become important. The different components of the sediment archive are not independent of each other, they are interlocking. The turbidite layers tell you about earthquakes, but they also complicate the age model for the sediment column by introducing material that was transported from elsewhere and deposited rapidly, potentially mixing sediment from different time periods. The tephra layers provide time markers, but they also need to be interpreted carefully in terms of how much ash was deposited and whether it was reworked by bottom currents before settling. The organic carbon record is sensitive to diagenetic processes, the chemical changes that occur in sediment after deposition, which can alter the original signal if the sediment has been exposed to certain conditions. Extracting clean, reliable information from a trench sediment core is not a simple matter of drilling down and reading the layers like pages in a book. It requires careful sampling, careful analysis, and careful interpretation of the ways in which the different signals in the sediment may have been modified or overprinted since they were first laid down. Getting the sediment in the first place is the part that the trench makes difficult. Sediment coring at Hadal depths requires equipment that can reach the bottom intact, penetrate the sediment to a useful depth, typically at least a metre and ideally several metres, collect the core without disturbing the layering, and return to the surface with the sediment preserved in its original condition. Various coring systems have been developed for deep-sea work. Gravity corers, which fall freely and use their own weight to drive a tube into the sediment. Piston corers, which use a triggering mechanism to create suction that pulls a longer core into the tube, and more specialised systems designed for particularly soft or particularly stiff sediment types. At full ocean depth, the challenge is not just the pressure, though the pressure is significant. It is also the reliability of the triggering mechanisms, the integrity of the core liner, and the behaviour of the sediment itself as it is collected. Trench sediments are often soft and water-saturated near the surface, which means they can flow or deform during recovery if the coring system is not well designed for those conditions. Deeper in the core, the sediment may be more compacted, requiring more penetration force. The core must be recovered without the bottom of the tube being lost, a frustratingly common failure mode, and without the sediment being mixed or disturbed during the ascent through 4 or 5 kilometres of water column. The seismic environment of the Kuril Kamchatka Trench adds another layer of complication. In a geologically quiet trench, the sediment record may be relatively undisturbed between major events, with clear, horizontal layering that is straightforward to interpret. In the Kuril Kamchatka system, the frequency of large earthquakes means that turbidite events are relatively common in the geological record, and the trench floor in some areas may have been repeatedly disturbed by sediment transport events over the past several thousand years. In those areas, the sediment column may contain multiple turbidite layers stacked closely together, with relatively thin intervals of background hemipelagic sediment between them. Interpreting the age and origin of each turbidite layer and determining which earthquakes they correspond to requires correlating cores from multiple locations along the trench, because a turbidite generated by a rupture on one segment of the fault may not extend to other segments, while a turbidite that appears at multiple sites along the trench is more likely to represent a very large, along-strike rupture. That kind of spatial correlation requires multiple cores from multiple locations, which requires multiple deployments of coring equipment, which requires multiple expeditions with favourable weather windows and functioning equipment, and the logistical and political access to operate in these waters. Some cores have been collected from the Kuril-Kamchatka Trench and from the surrounding abyssal plain. Soviet expeditions in the 1950s and 1960s collected sediment samples, though the coring technology of that era had limitations in terms of penetration depth and sample preservation. More recent work, including expeditions by Japanese and Russian institutions, has added to the core library. Researchers have used these cores to reconstruct earthquake sequences going back several thousand years, and the results have been scientifically valuable. They have extended the seismic record beyond the instrumental period and provided evidence for large prehistoric earthquakes that are not documented in any historical source. But the spatial coverage of the existing core collection is limited. The trench runs for over 2,000 kilometres, and the number of cores that have been collected from the trench floor itself, as opposed to the surrounding abyssal plain, where coring is somewhat easier, is small enough that large segments of the trench remain unsampled. There is also the question of what happens to the sediment record in areas where the trench floor is particularly tectonically active. Near the deepest parts of the trench, where the subducting Pacific plate is bending most steeply downward, the seafloor is cut by faults and fractures that can offset sediment layers and complicate the stratigraphy. In those areas, a sediment core might penetrate a sequence that has been tilted, faulted, or mixed by tectonic deformation, making it difficult or impossible to reconstruct the original depositional sequence. Identifying which areas of the trench floor have relatively undisturbed sediment records, and which areas are too tectonically disturbed to yield clean stratigraphic information, requires enough spatial sampling to map the variability, which is itself a significant undertaking. What all of this means, practically, is that the sediment archive of the Kuril-Kamchatka Trench is enormously valuable and only partially read. The information it contains about the earthquake history of one of the world's most seismically active subduction zones, about the volcanic history of the Kuril and Kamchatka volcanic arc, about the changes in ocean productivity and climate in the northwestern Pacific over thousands of years, is the kind of information that researchers in seismology, volcanology, paleoceanography and climate science all have reasons to want. Some of it has been accessed, some of it has been carefully analysed and published, but the coverage is thin, the spatial gaps are large, and the difficulty of collecting new material from the trench floor means that filling those gaps will require sustained, well-funded, technically capable effort over many years. The sediment sits there in the meantime, accumulating new layers at the top, while the older layers below continue to hold their records intact, largely undisturbed by anything except the occasional earthquake that deposited them in the first place. It is patient in a way that science cannot always afford to be, and the gap between what the trench floor is recording and what researchers have been able to read from it is, in its own quiet way, one of the more striking illustrations of how much of the deep ocean remains beyond what current exploration efforts can realistically reach, which brings the story, naturally, to what those efforts actually look like right now, and what they might look like in the years ahead. So what does current exploration of the Kuril-Kamchatka Trench actually look like? The honest answer is that it looks modest. It looks like small teams working with limited budgets and narrow weather windows, deploying instruments that cover a tiny fraction of the trench on each expedition, and returning with data that is valuable but incomplete. It looks like progress, but slow progress, the kind that accumulates over decades rather than years, and that rarely produces the kind of dramatic single expedition discovery that attracts broad attention. That is not a criticism. It is simply what deep ocean science in a difficult, remote, politically complicated environment tends to look like in practice. The Shirshov Institute of Oceanology in Moscow has been the primary Russian institution conducting oceanographic work in this region since the Soviet era. The institute carries on some of the research traditions established by the Vityaz expeditions of the 1950s and 1960s, though with considerably more constrained resources than the Soviet program had at its peak. Russian research cruises to the Kuril-Kamchatka region have continued periodically in the decades since the Soviet collapse, collecting water column data, biological samples, and some sediment material. The work is real and scientifically meaningful, but the frequency of expeditions has been limited by funding, and the depth capabilities of the available vessels and equipment have not always been sufficient to reach the deepest parts of the trench with the tools needed to do the most scientifically demanding work. There are years when no significant cruises go to this specific trench at all. The institutional knowledge is there, the motivation is there, the consistent resources have been harder to sustain. On the Japanese side, JAMSTEC, the Japan Agency for Marine Earth Science and Technology, has been the most technologically capable institution working in the broader region. Japan has strong scientific and practical reasons to understand this trench. The subduction zone that created it is part of the same tectonic system that runs along the Japanese archipelago, and the earthquake and tsunami hazard that system generates is a matter of direct national concern. JAMSTEC has conducted expeditions to the Kuril-Kamchatka Trench system using its research vessels and deep-sea instruments, including lander deployments and some acoustic mapping work. The Institute's scientific output from the region includes biological studies, sediment work, and bathymetric data that has improved the detail of trench floor mapping in certain areas. The loss of the ROV Kaiko in 2003, the vehicle that had made the deepest dive in history to the Mariana Trench in 1995, was a significant setback for Japanese full ocean depth capability, and the gap between Kaiko's loss and the development of successor systems meant that full depth access was interrupted for years. JAMSTEC eventually developed the ROV Kaiko Mark IV and later the hybrid ROV Nereid, though the full ocean depth program has continued to face the technical and financial challenges that affect all deep Hadal research programs globally. One of the more practical tools that has been used with some success in this trench is the autonomous lander. A lander, in this context, is a relatively simple instrument platform. No thrusters, no real-time piloting, no tether. It is weighted to sink to the bottom, where it sits for a predetermined period, collecting whatever data or samples it is designed to collect, and then releases its ballast weight and floats back to the surface. The simplicity is the point. Without a tether, there is no cable to fail, and no surface ship that needs to maintain precise position above the instrument for hours or days. The lander descends on its own, does its work, and comes back up when the timer triggers the ballast release. Recovery requires finding it at the surface, which is done using acoustic transponders and sometimes a radio beacon and a light for visual location. Landers equipped with bait cameras have been deployed in the Kuril-Kamchatka Trench and have returned footage of the biological communities at depth. The amphipods arriving in large numbers within minutes of the bait being detected, the sea cucumbers moving slowly across the sediment in the background, the occasional fish at shallower Hadal depths. This footage is genuinely useful scientifically, and it is gathered at a fraction of the cost and complexity of an ROV dive. The limitation is that a lander cannot move. It samples one spot. It cannot follow an interesting feature across the seafloor, cannot collect a targeted sediment sample from a specific layer, cannot respond to what it sees. It is a fixed observer rather than an explorer. For a trench that stretches over 2,000 kilometers, a lander tells you what is happening at one point on one day. That is valuable, but it is a narrow window. Acoustic mapping from surface ships has been another important tool. Multi-beam sonar systems mounted on research vessels can map the bathymetry of the trench floor, the shape of it, the depth variations, the large-scale structure, without any instrument ever descending to the bottom. A ship travelling at normal survey speed can cover large areas in a relatively short time, and modern multi-beam systems produce high-resolution maps that reveal ridges, fault scarps, sediment fans, and other large-scale features with considerable detail. This kind of mapping does not tell you what the biology is doing or what the sediment chemistry looks like, but it tells you where things are. It gives scientists the spatial framework needed to plan targeted sampling, to identify the most scientifically interesting locations, and to understand the overall architecture of the trench system. Some multi-beam mapping has been done in the Kuril Kamchatka Trench, and the available bathymetric data has improved significantly from what existed in the early post-Soviet period. But coverage is still uneven. Parts of the trench have been mapped at reasonably high resolution. Other parts remain known only from older, lower resolution datasets that leave significant uncertainty about the actual depth and shape of the seafloor in those areas. The full high-resolution bathymetric map of the entire Kuril-Kamchatka Trench does not yet exist. It is worth pausing on that for a moment. We are talking about a structure that is over 2,000 kilometers long, up to 10.5 kilometers deep, and one of the most geologically significant features in the Pacific Ocean, and we do not have a complete, high-resolution map of its floor. There are portions of this trench where the best available depth data comes from measurements made by Soviet vessels in the 1950s and 1960s using technology that, by modern standards, was relatively coarse. That is not a failure of any particular institution or program. It is simply an illustration of how large the trench is relative to the resources that have been directed at it. The 5 Deeps expedition, which ran from 2018 to 2019, demonstrated something interesting about the current state of deep ocean exploration. The expedition, funded privately by the American investor Victor Vescovo, aimed to reach the deepest point in each of the 5 oceans using a purpose-built full ocean depth submersible called the Limiting Factor. The Limiting Factor was designed and built by Triton submarines and was capable of reaching any depth in the ocean, the first crewed vehicle to be certified for full ocean depth operations since the Trieste in 1960. The 5 Deeps expedition did not include the Kuril-Kamchatka Trench in its primary mission profile. It focused on the Puerto Rico Trench, the South Sandwich Trench, the Java Trench, the Malloy Deep in the Arctic, and ultimately the Challenger Deep in the Mariana Trench. But what the expedition demonstrated was that private funding, combined with modern engineering and careful planning, could produce a vehicle capable of reaching any point in the ocean and doing so repeatedly. The Limiting Factor made multiple dives to full ocean depth, collected scientific data, and survived. That had not been done before in that way. The scientific program attached to the expedition collected new biological and bathymetric data from several of the target locations. The model, private funding enabling a scientific capability that government programs had not been able to sustain, attracted attention in the oceanographic community as a possible template for future work. Whether that template will be applied to the Kuril-Kamchatka Trench is an open question. The political access issue does not disappear, because the funding is private. A private expedition still needs permission to operate in Russian-controlled waters, still needs to navigate the sensitivities around the Kuril Islands dispute, still needs a weather window in one of the stormiest ocean regions on Earth. The technology barrier is, in some ways, the easier part of the problem. The Limiting Factor exists. Other full ocean depth vehicles are in development or have been built by Chinese and other national programs. The Woods Hole Oceanographic Institution has been developing new deep-capable systems following the loss of the Nereus in 2014. The engineering challenge of building a vehicle that can survive 10,000 meters of pressure has been solved, at least in principle. The challenge of getting that vehicle to the Kuril-Kamchatka Trench and operating it there under realistic conditions is a different kind of problem, and it involves factors that no amount of engineering can entirely resolve. New generation autonomous underwater vehicles, AUVs, are also part of the picture. Unlike ROVs, which are tethered to a surface ship, AUVs operate independently, following pre-programmed routes or making onboard decisions based on sensor data. They can be designed to operate at Hadal depths, though full ocean depth AUVs are still rare and expensive. The advantage of an AUV over a lander is mobility. It can travel along the trench floor, mapping a transect, collecting water samples at different depths, or following a chemical gradient toward a biological hotspot. The disadvantage compared to a crewed submersible or a piloted ROV is that an AUV cannot respond in real time to unexpected observations. If it encounters something interesting that was not anticipated in the mission plan, it continues on its programmed route unless the onboard decision-making system is sophisticated enough to recognize and respond to the anomaly. That kind of onboard intelligence is improving, but it is still limited. For exploratory science in an environment as poorly characterized as the Kuril Kamchatka Trench, the ability to respond to what you're actually seeing, to stop, look more closely, collect a sample from a specific spot, follow a feature that was not on the map, remains a significant advantage of human-piloted or remotely piloted systems over fully autonomous ones. Some researchers have argued that the most productive near-term approach for this trench is a systematic combination of methods: multi-beam mapping from surface ships to build a complete high-resolution bathymetric base map, lander deployments to characterize the biology and chemistry at multiple locations along the trench, targeted AUV transects to map specific areas of scientific interest in more detail, and occasional ROV or submersible dives to the most scientifically compelling locations for direct observation and sampling. Each of these methods has different cost profiles, different logistical requirements, and different scientific returns. Used together, they could build a progressively more detailed picture of the trench without requiring any single expedition to do everything at once. The challenge is that even this more incremental approach requires sustained funding, sustained access, and sustained scientific coordination between the institutions that are best positioned to contribute, which, in this case, means primarily Russian and Japanese institutions working in a political environment that has not always been conducive to that kind of collaboration. There have been periods of improved scientific cooperation between Russia and Japan in the oceanographic sphere. Joint research programs have existed, and some collaborative cruises have taken place. The underlying territorial dispute over the Kuril Islands has not been resolved, and it continues to cast a shadow over the relationship, but science has occasionally found a way to proceed in parallel with unresolved political questions. Whether the current geopolitical environment allows for that kind of pragmatic scientific cooperation is a question that goes well beyond the trench itself. What is clear is that the pace of progress, measured against the size of what remains unknown, is slow. The trench is not being ignored. There are scientists who have devoted significant parts of their careers to understanding it, institutions that return to it when resources allow, and a body of published research that has grown steadily over the decades. The biological communities of the Kuril-Kamchatka Trench are better understood than they were 20 years ago. The bathymetric data is better than it was. The sediment record is more extensively sampled. The picture is sharper than it was, even if it remains incomplete. That is real progress, and it is worth acknowledging. But the trench is also larger, deeper, more geologically complex, and more difficult to reach than almost any other structure on Earth. The gap between what is known and what could be known is not closing quickly. And the reasons for that, the weather, the politics, the technology, the funding, the sheer physical scale of the place, are not going away on their own. There is something almost stabilizing about that, in a strange way. The trench will still be there. It is not going anywhere on any timescale that matters to the people working on it. The sediment is still accumulating. The amphipods are still moving across the floor in the dark. The fault structures are still being stressed by the ongoing subduction of the Pacific plate. Whatever is down there that has not yet been found is still down there, undisturbed, waiting with the particular patience of things that have no awareness of being waited for. The science will continue to inch forward, one expedition at a time, one recovered lander at a time, one sediment core at a time, and the realistic near future of Kuril-Kamchatka exploration is probably not a single dramatic breakthrough, but rather a gradual accumulation of pieces, each one small, each one meaningful, and each one adding a little more resolution to a picture that is still, in most of its details, not yet fully visible. That slow accumulation is, in its own way, what deep ocean science has always looked like. And the Kuril-Kamchatka Trench, for all the specific reasons that make it harder than most, is ultimately part of that same long, patient project of trying to understand what the bottom of the ocean is actually like. Which, when you consider everything that has been laid out here, the geology, the history, the politics, the technology, the biology, the sediment, brings the story to a natural place to reflect on what all of it, taken together, actually means. And so, here we are, at the edge of what can be said about a place that has barely been touched. The Kuril-Kamchatka Trench is, by almost any measure, one of the most significant geological structures on this planet. It is roughly 2,200 kilometers long. It reaches more than 10,500 meters at its deepest confirmed point. It was formed by forces that have been operating continuously for tens of millions of years and will continue operating for tens of millions more. It sits at the intersection of some of the most violent seismic and volcanic activity on Earth, surrounded by some of the most productive surface waters in the ocean, under some of the most consistently hostile weather in the northern Pacific. And most of it has never been seen by anyone. That is not a dramatic overstatement. It is just a fact, and it is worth sitting with for a moment before moving on. When you add up everything that has been covered here, the subduction geology, the seismic history, the crushing pressure and near-freezing temperatures of the Hadal Zone, the Soviet research programs that built the early knowledge base and then largely dissolved, the territorial dispute that has cast a shadow over international access for decades, the surface storms that make even reaching the site a serious undertaking, the handful of full ocean depth vehicles in the world and the ones that have been lost, the biology that has been sampled from a vanishingly small fraction of the trench floor, the sediment archive that holds thousands of years of earthquake and volcanic history. What you get is not a simple story of neglect or missed opportunity. It is something more complicated than that. It is the story of a place that has resisted being known, not through any single dramatic barrier, but through the accumulation of many overlapping difficulties, each one manageable in isolation, but collectively forming something that has proven, so far, to be very hard to overcome. There is a particular kind of scientific frustration that comes from knowing something important is there, being able to describe its outlines with reasonable confidence, but being unable to get close enough to see it clearly. The researchers who work on this trench know what kinds of things are likely to be found there. They know, from analogy with other Hadal systems and from the limited sampling that has been done, that the biology is rich and strange and probably includes species that have not been described. They know that the sediment record contains a detailed history of earthquakes and eruptions that could help improve hazard models for one of the most seismically active regions on Earth. They know that the trench floor has geological features, fault structures, sediment plains, possibly hydrothermal activity in some areas, that would be scientifically valuable to observe directly. They know all of this in general terms. What they mostly do not have is the specific, detailed, ground truth knowledge that only comes from actually being there, from sending instruments to the bottom and recovering them, from looking at footage and samples and measurements taken from the trench itself rather than inferred from models and analogies. That gap between general knowledge and specific knowledge is exactly what makes the Kuril-Kamchatka Trench so representative of something broader. It is not the only place on Earth where that gap exists. The deep ocean as a whole remains poorly mapped and poorly understood. More of the surface of Mars has been mapped at high resolution than the floor of Earth's oceans. The Kuril-Kamchatka Trench is an extreme case of a general condition. The condition of a planet whose interior, whose deep waters and whose most remote and hostile environments are still mostly beyond what humans can practically and continuously observe. There is something humbling about that, and not in a performative way. It is genuinely humbling. The trench has been there since before the Himalayas existed in their current form. The Pacific plate has been sliding under the Okhotsk plate since long before any human ancestor walked upright. The amphipods moving across the floor of the Vityas deep in the dark, the ones that have been collected in baited traps and identified and described in published papers, they are part of ecosystems that have existed in some form for far longer than the species that is now trying to understand them. The trench does not need to be explored. It is not waiting to be discovered in any meaningful sense. It exists completely independently of whether anyone ever reaches the bottom of it, and yet the impulse to understand it is not trivial. The earthquake history preserved in those sediment layers is not just scientifically interesting in an abstract sense. It has direct relevance to the communities that live along the coasts of the northwestern Pacific, communities that have been hit by tsunamis generated in this region and will almost certainly be hit again. The better scientists understand the recurrence intervals and magnitudes of past events in this subduction zone, the better the probabilistic models for future events, and the more time there might be to prepare. That is a practical human reason to care about a place that is otherwise defined by its remoteness and inaccessibility. The biology matters too in ways that are harder to quantify but no less real. The Hadal zone is one of the least understood biological environments on Earth. The organisms that live at full ocean depth have evolved solutions to pressure, temperature, and food scarcity that are genuinely unusual, and some of those solutions have already yielded insights relevant to biochemistry and material science. The enzyme systems of pressure-adapted bacteria, the structural adaptations of amphipods that can survive pressures that would instantly destroy most cellular machinery, these are not just curiosities. They are data points in a much larger project of understanding how life works at its physical limits. The Kuril Kamchatka Trench, with its high surface productivity feeding organic material down into the Hadal zone, is probably one of the more biologically active deep trenches on Earth. The fraction of that biology that has been sampled is, to put it plainly, tiny. So what the trench represents in the end is a kind of unfinished question. Not a mystery in the dramatic sense. There is no lost civilization at the bottom, no secret waiting to be dramatically revealed. Just a very large, very deep, very complex natural system that has not yet been adequately described, for reasons that are mundane and structural and in several cases entirely political rather than scientific. The knowledge is wanted. The tools to gather it, at least in partial form, exist or are being developed. The obstacles are real, but not permanent, and the science, as it always does, will continue to inch forward. What the trench also represents, maybe more quietly, is the particular patience that deep science requires. Not the patience of waiting for a dramatic moment, but the patience of returning year after year with whatever resources are available, adding one more sediment core, one more lander deployment, one more sonar transect to the cumulative record. The Soviet scientists on the Vityas in the 1950s were doing that kind of work. The Jamstek researchers who have conducted expeditions in this region in more recent decades are doing that kind of work. The researchers at the Shushoff Institute who have continued periodic cruises, despite funding constraints that would have stopped less committed programs, are doing that kind of work. None of it produces a single definitive image of the trench floor. All of it contributes to a picture that is, slowly and incrementally, becoming more detailed. There is something worth appreciating in that, even if it does not make for a dramatic story. The history of deep ocean science is largely a history of that kind of patient accumulation. The great depths were not understood all at once. They were understood piece by piece, expedition by expedition, instrument by instrument, over more than a century of effort by people whose names most of us will never know. The Kuril-Kamchatka Trench is part of that same long project, still in relatively early chapters, with most of its story still unwritten. If you have stayed with this all the way through the geology and the earthquakes, the Soviet expeditions and the Cold War politics, the pressure calculations and the imploded ROVs, the amphipods in the dark and the turbidite layers in the sediment, then you have spent time with a place that most people have never heard of, thinking about questions that most people never think about. And that in itself seems like a worthwhile thing to do. The trench will still be there tomorrow. The Pacific plate will still be moving westward at roughly 8 centimeters per year, slowly and relentlessly driving under the Okhotsk plate, building stress in the fault structures that will eventually release in earthquakes that will shake the Kuril Islands and send waves across the Pacific. The water at the bottom of the Vityaz Deep will still be just above freezing, still under more than 1,000 atmospheres of pressure, still completely dark. Whatever lives down there will still be going about whatever it is they do, entirely unaware that anyone has ever wondered about them. And somewhere, in a research institution in Yokohama or Moscow, or perhaps somewhere else entirely, someone is probably looking at funding proposals or weather forecasts or equipment specifications, planning the next time they might be able to go back, not to solve the trench all at once, just to learn a little more. That is how it goes. That is how it has always gone. And there is something genuinely comforting in that if you let it be. Thank you for spending this time here. If something in this story surprised you, the depth of the Soviet research program, the political complications that have lasted since World War II, the biological richness of a place so hostile to almost everything, it would be lovely to hear about it in the comments. This channel exists because of the people who find these quiet, overlooked corners of the world worth sitting with for a while. If you have not already subscribed, this might be a good moment. There is more to come, and it is always better shared. Take care of yourselves wherever you are tonight.